Dear colleagues, I have the honor to chair the 7th HealthyIoT conference, sponsored and supported by European Alliance for Innovation. The conference was originally planned to be held in a physical form in Portugal, one of the most beautiful countries in Europe. Unfortunately, due to current pandemics, we had to cancel the physical event and to migrate to the online format. We hope that the science and nature will win this battle against COVID-19 in the next few months, so we can meet next year to discuss the experiences we gather and to plan the future. I have to thank the organizing and technical program committee members for great work they did on organizing this conference. It was a very challenging task, having in mind these extreme conditions we were all exposed to. Also, I have to thank the reviewers for doing great and very hard work on selecting the papers that are more appropriate for publishing at this moment. I thank the authors for recognizing this conference as the best way to share their results and contribute to fighting traditional but also some novel problems in this domain. Also, I thank the European Alliance for Innovation for establishing and supporting the HealthyIoT conference for over these 7 years. I have to thank Professor Mladen Vojinovic for chairing a panel at this conference. We had the extraordinary panelists, Professor Zona Kostic from Harvard University, Professor Nuno Garcia from Portugal, Professor Ivan Čorbe from North Macedonia, Professor Igor Kotsiuba from Ukraine. This panelists gave us great insights on using the latest technologies to fight current and future pandemics. I have to also express my gratitude to Professor Susanna Spinsante and Professor Bruno Silva, the conference co-chairs, for their dedication and enormous work they did. In order to keep established high-quality standards of the HealthyIoT, we had to respect acceptance rate and to, unfortunately, reject many pretty good papers. These papers were just relatively slightly less sound than the accepted papers, and in most cases they had just some minor flaws. So I encourage the authors of the rejected papers to improve them according to the reviewers' comments and to submit them to great journals and conferences available in this period, or to save them for the next year HealthyIoT. So let me officially open the HealthyIoT 2020 conference. I'm sure you'll enjoy the presentations and the panel and have an opportunity to meet and talk to some extraordinary people. I wish you a pleasant and successful day.
Dear ladies and gentlemen, let me welcome you to the EAI HealthyIoT 2020 conference held in this virtual interactive setting. I am Viltare Platzner and I would like to address all of you on behalf of EAI and HealthyIoT 2020. I would like to use this opportunity to address the organizing committee, the authors and all the participants on behalf of all of us here at EAI. I would like to thank all of you for being part of this conference and for your involvement with EAI. In particular, I would like to thank the General Chair Aleksandar Jevremovic, Susanna Spinsante and Bruno Silva, and the Program Chair Nuno Pombo, together with the whole organizing committee, for their excellent work during the conference preparation. Today, during this streaming, we would like to invite you to participate in the Q&A sessions. During each video, please write your questions about the current presentation into the chat window. After the presentation is done, the session chair will ask selected questions to the author of the presentation in a live conversation. Lastly, I like to use this message to invite you to join us again at the EAI HealthyIoT 2021. Should you be interested in becoming a part of the next year's conference, please do not hesitate to contact us at the email address below. Similarly, if you are interested in discussing other possible cooperation, conference, workshop, or a new event altogether, please contact us at this email address as well. Thank you for your attention and enjoy EAI Healthy IoT 2020.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work-in-progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hello everyone, welcome to this presentation. The title of our paper is a non-invasive, cloud-based IoT system and data analytics support for women struggling with drug addiction during pregnancy. The authors of this paper are V. Balogun, O.A. Sarumi, and O.D. Balogun. The presenter is O.A. Sarumi. Here, we present the problem statement for this research. Drug abuse among pregnant women and the subsequent neonatal illness are very important clinical and social problems. The upsurge in the use of dangerous drugs among pregnant women put an increasing number of children at a risk of birth developmental problems. For example, birth deformities, low birth weight, mental disabilities, among others. There are social determinants of health that prevent addicted pregnant women from accessing treatment programs, as presented in Sharaman et al. 2017. Among these are fear of stigmatization, fear of their babies being taken away by the child families services, fear of confinement to a facility for addiction treatments, lack of access to specific treatment programs for addiction, lack of support from partners or family members. Also, the onset of COVID-19 has impacted the accessibility and retention of pregnant women to treatment programs, as presented in Hillary 2020. Here, we present our proposed solution to the identified problems of the existing system. We propose a non-invasive, cloud-based Internet of Things and data analytics framework to provide support for pregnant women seeking addiction treatment. The system uses integrated sensors in a smartwatch to monitor, collect, and process vital data from pregnant women to identify instances of emergencies. During emergencies, the system automatically contacts specific needed service or services and send processed data to the cloud for storage and data analytics to provide deeper insight and necessary decision making. Also, the framework ensures that the pregnant women are not coined into a facility and are reachable remotely by healthcare practitioners during pandemics like COVID-19. Here we give a brief background of IoT in healthcare. IoT, that is Internet of Things, is a network consisting of several devices interacting together in a machine-to-machine communications with the aim of collecting and exchanging vital information. It has potential for enabling patient health monitoring applications that can be streamlined in real time to health practitioners, especially during emergencies. Like you know, human body parameters can be measured by sensors and portable devices without human intervention. Handling the massive IoT-based healthcare data can be really challenging. Therefore, cloud computing can be used as a backbone network to provide storage and network service support for IoT healthcare systems. Also, bringing in fog computing brings the cloud closer to the network user, thereby providing a real-time processing, reduce network latency, improve data privacy, and reduce costs of implementation. Here we present some related work. In the work of Farani et al., they introduced a systematic IoT e-health ecosystem made of hardware and software devices without a specific implementation of such IoT models. Also, Kumari et al. Presented a three-layer healthcare architecture for real-time applications that include a fog computing layer. Also, Dang et al. Described a system where a network of connected sensors record patient vitals and the data are continuously sent to a broker. The limitations of this system is that they were not investigated for supporting sensitive applications like monitoring of pregnant women with addiction problems, in which the patient cannot be attached with sensors that can easily be detached from the body during a medical crisis. Here we discuss the cloud-based IoT support for drug-addicted pregnant women. Healthcare support and monitoring system that confines the user to a restricted facility is not desirable for supporting drug-addicted women, especially during a period of COVID-19 like this. IoT systems that use sensors implemented on a circuit board or sensors that need to be attached to different parts of the body are also not desirable. Why? These sensors will constitute extra weight to the pregnant women. Also, attached sensors could be easily stripped off by the pregnant women, leading to monitoring failure. So we propose a IoT-enabled healthcare support system that uses a smartwatch embedded with essential sensors that monitors the behavior of the pregnant women during drug overdose or when exhibiting withdrawal symptoms. It also provides the pregnant women with a non-invasive and a portable monitoring system that allows the user to go about their day-to-day activities while receiving addiction treatment. To the best of our knowledge, this will be the first time that a non-invasive cloud-based IoT healthcare system service delivery is being considered for supporting pregnant women struggling with drug misuse. The architectural framework for our research is presented in this slide. The architecture consists of 4 key layers, which include the wide body area network or the sensor layer, a cloud computing layer, the edge or fog computing layer, and the medical service layer. In the next few slides, we are going to explain details of how these layers interact and communicate together. The sensor or wide body area network layer is where health-related data are collected from the body of the users with the aid of sensors embedded within the smartwatches worn by the users. The personal server or 4 computing layers serve as the link between the sensor layer, the medical service layer, and the cloud computing layer. Health-related data collected by the sensors are sent using the short-range ZigBee or Bluetooth wireless technology to the pregnant woman's smartphone, which will serve as the gateway. Sensor readings are collected at this layer for immediate processing and integration of data to provide real-time insight and decision-making about the state of the user. Pregnant women could be provided with audio and graphical interface to disseminate alert messages or needed guidance during medical crisis. When the user is expecting medical emergency as indicated by the analyzed data, the personal server layer will establish a secure long-range internet communication with the medical service layer and allow the respective remote healthcare service provider. The medical service layer allows real-time monitoring of the patient by service provider including gynecologist, obstetrician, general physician, emergency response team, health community workers, family, and friends. They will have access to a cloud-enabled centralized medical database that provides historical data and results of analysis of both current and previous data collected by the IoT system. This provides real-time access to vital medical information about the patient, providing deeper insight and decision-making functionality based on the result of the big data analytics done in the cloud system, and prevent double doctoring, which can lead to multiple prescriptions of the same medication. Also provides swift medical support for COVID-19 infected pregnant women with underlying medical conditions. The cloud computing layer serves as the center where the massive physiological data are aggregated, stored, processed, and analyzed to provide support to healthcare service providers. Also hosts a centralized medical database where both historical and current medical data are stored for centralized access by medical practitioners and other healthcare providers. Furthermore, machine learning algorithm is engaged to allow the system to learn from the past and current data in order to make predictions and provide vital information about the patient's symptoms and possible diagnosis. This also allows the identification of trends in medical physiological data that were formerly unidentified to provide specific diagnosis, treatment plans, and decision support for healthcare service providers. The big data collected from the addicted pregnant women will be a good platform for fine-grained data analytics that will provide deep insight on the pregnant women's health status. This can provide intelligent recommendations for the physician, emergency support unit, and other healthcare service providers. The data analytics component will employ several data merging techniques such as feature extraction and dimensionality reduction to optimize the data and ensure that noise and redundancy are eliminated from the data. Our machine learning algorithm include neural network and decision tree that allow the system to learn from the past and current data for enhanced predictive analytics. Data mining techniques such as association rules will be employed to identify trends in medical physiological data that were formerly unidentified to provide specific diagnosis, treatment plans, and decision support for healthcare service providers. A lightweight predictive algorithm is deployed at the fog layer to provide immediate and on-demand healthcare services to the users. Our proposed system will profit from the implementation of big data processing frameworks, including Apache Spark and Apache Kafka, to speed up the data analytics process and provide a platform for enhanced scalability as the size of the healthcare-related data increases. In conclusion, in this research, we presented a non-invasive, cloud-based IoT healthcare infrastructure for supporting pregnant women seeking treatment from drug misuse during pregnancy and public emergencies like COVID-19. The novelty of our proposed system stems from its ability to allow pregnant women seeking addiction treatment to continue with their normal daily activities while receiving intensive healthcare support without being confined to a facility. The system also profits from real-time local data analytics at the fog layer, as well as the extensive data analysis at the cloud layer. The local data analytics provide immediate services to the pregnant women, while the extensive cloud-based data analytics provide a long-term support for the pregnant women as well as the supporting healthcare service providers. In our future work, we are going to present a detailed description of our data analytics approach for the work. Also, in our future research, we plan to implement the IoT-based healthcare system with the aim of evaluating its efficiency and effectiveness in supporting the intended users. We will also consider relevant security and safety issues that have to do with the usage of proposed systems, especially during global pandemics like COVID-19. Thank you for listening.
Hello, this is Alessia Pagliaronga from the National Research Council of Italy. In this talk, I'll outline the main developments towards the dedicated smartphone app for hearing screening. This is a collaboration between the National Research Council of Italy and the Biomedical Engineering Department at Politecnico di Milano. A brief outline of the talk. Well, first, I'll discuss the overall context and the needs that we have identified in the area of adult hearing screening. Then we have identified the design criteria for the smartphone app development. Particularly, we aimed at a language-independent speech-noise test, so viable for use in individuals of unknown language globally. Moreover, we have developed a novel adaptive procedure, an automated adaptive procedure that is faster compared to conventional ones and accurate. We have tested performance, accuracy, and reliability in repeated measures in a wide group of subjects. Also, we have addressed the viability for remote testing, which is a crucial part in a smartphone app development. Then I'll draw the conclusions and discuss the most important future development of this work. Well, the overall context in the area of hearing screening is that, well, we need methods for hearing screening. Hearing loss is a problem. It is typically neglected, or it is typically accepted. So there's a huge need for hearing screening methods, particularly at a distance. Well, first, we need to test speech recognition. So not only pure tone thresholds, which is the standard clinical assessment method. We need to test speech recognition to reflect the real lived difficulties related to hearing handicap. Well, speech is inherently language dependent, but we are trying to develop a test that can be used across language. So we developed a set of stimuli and a procedure that can be performed by individuals who are not native language, and whereby understanding of the meaning of speech stimuli is not required. Third, we want to test at a distance, which is crucial for smartphone app development. So we have introduced a sort of compensation of output levels to account for the different environmental settings that the test can be used. Regarding the design criteria that are drawn from the previously identified needs, well, testing speech recognition means that we should use speech material that is sensitive to the early difficulties. So the most important difficulties that tell us that the problem does a sort of hearing problem. And this typically occurs with, for example, short transients, consonants, fast parts of speech. Moreover, we need an accurate and reliable procedure that can be used in repeated measures and be consistent for monitoring, for example. Second, we wish to test in multilingual settings, as said. So this means that we need speech that do not convey any meaning, that do not require knowledge of language, knowledge of vocabulary, and do not require understanding. So we've introduced the multiple choice task. Third, testing at a distance. Well, that means that we cannot have an experimenter, an operator. We need an automated test that is user-operated and needs to be easy to use. We want the test to be short, to reduce fatigue, annoyance, and also learning effects that may occur on repeated measures. And we need the test to be accurate in various environments, so both controlled and uncontrolled settings. These are the main targets of our work. Let's see where we are now. Regarding the speech material and the recognition task, we are not using words that are typically language dependent. We are not using sentences or speech stimuli with meaning. We are using vowel, consonant, vowel words, meaningless words, sort of aba, ata, asa. And we are using a 3 alternatives forced choice task. So the subject doesn't have to repeat the word. The subject has to select between 3 alternatives. So those kind of stimuli are important as they are sensitive to the earlier difficulties. The earlier clues of age-related hearing loss are basically related to consonant recognition, decreased consonant recognition. Also, meaning is not important in the stimuli, so we have limited the higher level processing, the influence of language, and the influence of culture and literacy. So we wish the test to be as easy to use as possible, as easy to understand as possible. And that's the main concept. We have tested the eligibility of VCV across language, because we have recorded a large corpus of stimuli from native speakers, professional native speakers of 5 different languages, among the most widely used globally. English first, French, German, Italian, and Portuguese. We have recorded a set of VCVs based on 12 common consonants, B, D, F, G, K, L, M, N, P, R, S, T. We have recorded, of course, by following the technical standards, and we have tested the intelligibility of those stimuli in 2 different ways. We've used objective measures, the STORY measure, short time objective intelligibility, and we have used subjective measures. We have run speech recognition tests. These are from our previous studies. I'm only going to summarize the main outcomes. So we have identified the best candidate set of VCV, which is the one spoken by the English speaker. So in the development of the test, we have used a set of 12 consonants in the context of the vowel A, spoken by an English professional male speaker. We now combine with noise, as our test is a speech in noise test. So basically the noise is generated as a speech-shaped noise by using the universal long-term average speech spectrum. So this is a summary of the processing path. The speech stimuli are combined with noise at different signal-to-noise ratios, SNR. Well, the SNR is not predetermined, it is determined adaptively during tests. The rationale is to adapt the SNR based on the specific answers given by the subject, and this is known as adaptive procedure. So we have developed a new procedure that is different than the conventional one. Typically, conventional staircase, adaptive staircase, change the output presentation level, so the SNR, by a fixed amount. So they use equal upward and downward steps, typically 2 decibels. This is based on the assumption that any stimulus in the set has the same intelligibility, so they can be sent interchangeably at the same SNR, reaching the same intelligibility. We know that this is not true, so we have developed a new staircase, which we call VAR, SNT VAR, speech noise text VAR, which does not use fixed steps, which does not use equal upward and downward steps, but it's using adaptive steps. So it is adaptive because it becomes more difficult if the subject gives correct responses, and it becomes less difficult if the subject gives wrong responses. But the degree of change in intelligibility changes based on a model, a psychometric model that we have evaluated. So in the picture, for example, you can see 4 different psychometric curves which are derived from the VCV stimuli that have been clustered in 4 subsets. And the test adapts the pathway by running across those psychometric curves until it reaches a final point. What we do is to use a variable step size. As you see from the green arrows and red arrows, the green may mean correct responses, decrease in intelligibility, and the red arrows mean wrong responses, so we need to increase the intelligibility. We're using an optimal ratio between the downward and upward steps, which is more or less 0.74, which is derived from literature. So by using this kind of ratio, we know that we need less reversals than the typical procedure, and we can reach the final point earlier than with conventional ones. Conventional ones need 20 reversals. Our circuit needs 12 reversals. Then we're estimating the SRT, which means speech reception threshold, from the average of the last 4 ascending runs. So the ratio is the key to a shorter path. We have compared the conventional and the newly proposed one, first on young normal hearing participants in lab settings. We have observed, well, on the left, you can see the speech reception threshold in the test and retest, in the conventional red and new procedure, blue. On the right-hand side, you'll see the test duration in the test and retest trials in the conventional red and new procedure blue. What we can see is that our new procedure shows accurate estimation of speech reception threshold, which is the same, basically, as the one measured with the conventional one, and higher test-retest repeatability, because the outcome of the first and second trial are basically the same average SRT and basically overlapping distributions. Regarding the test duration, we observed that our test is substantially shorter than the conventional ones, more or less 2 minutes shorter, so from 5 minutes and a half to about 3 minutes and a half, and again, similar test duration in test and retest. So the test is accurate, repeatable, and shorter in normal hearing participants. Then we developed some design principle for the smartphone app. This is a summary. In the end, we'll have a smartphone app, which in the main screen will show 3 alternatives for the recognition of PCV in a multiple choice task. We have introduced the efficient staircase procedure, just described, and we are introducing machine learning for classification of test outcomes into pass and fail. Pass means, okay, good screen outcome. Fail means, oh, there might have been problem in hearing. So this means recommendation to go further in assessing and having a hearing check clinically. So this is the main design concept of the app. In the end, we're going to have a screening outcome, pass or fail. Some screens from the prototype of the user interface. Again, the 3 alternative force choice screen with the 3 alternatives. On the left, volume control. I'll talk later about this. So the subject has the opportunity to adjust the volume before taking the test. So we have a volume level that can be adjusted by the subject at a comfortable level. And in the output, we have several outcome measures. The most important one is the speech reception threshold. This is a normal hearing subject, minus 14.75 decibels. We have many additional parameters: the number of correct responses, the percentage of correct responses, the threshold of intelligibility, the total duration, and so on. So in the classification task, we are going to use all of those parameters and some more additional parameters to try to optimize the classifier. In the first experimental validation, we have involved about 150 subjects, exactly 148. Some of them were tested in both years. Most of them were tested only in 1 year, so for a total of 156 years tested. The age range is from 20 to about 90 years, with a broad age distribution. We have many subjects above 60 and 70. And those speak very different languages: English, French, German, Italian, Spanish, Afrikaans, Filipinos, and some more. If we consider the speech reception threshold only as a criterion for classification of degree of hearing loss, we can build the ROC curves. There are 2 curves in this picture, the red and the blue one, depending on the degree of hearing loss. The WHO defines 4 different levels of hearing loss. Slight mild hearing loss means pure tone average above 25 decibels. Moderate hearing loss means pure tone average above 40 decibels. And then we have severe and profound, but so few subjects in those ranges because those are really debilitating hearing loss levels. We focus on slight mild and on moderate. However, screening should target the slight mild level. So the level of a slight level of hearing loss where the person is not yet aware or is not about to take action. Because in the moderate hearing loss, we are going to have some substantial difficulties. Well, the red and blue lines reflect the ROC for the mild, slight mild, and moderate hearing loss, respectively. We come up to a cutoff SRT to classify individuals into normal hearing or hearing loss. In this study, we have gone beyond classification based on SRT, as we want to classify by using a large set of variables. In addition to classification, we have considered test-per-test reliability, both in the small group of young normal hearing. And if we look at the repeatability of SRT, speech reception threshold, we can see that the mean and standard deviation in young normal hearing was 1.7 decibels SNR, with a standard deviation on 1.5. Coming to older adults, a small group involved in test-per-test was 21. We had, as expected, a higher mean absolute variation of SRT with a higher standard deviation. However, the average test-per-test change is lower than half decibel. And the correlation of SRT between test and retest is higher than 80%. We have also computed the Cohen's kappa for SRT classification into pass-fail, getting a 0.8 Cohen's kappa, which is a very good level. Also, we see that the test performance is quite stable in terms of number of stimuli, test duration, and correct responses. In test and retest, particularly, the percentage of correct responses will be basically the same in test and retest. Regarding classification into pass-fail, we have used a large set of features that come from the user interface and software. First of all, the SRT, but also the age of the subject, which is important, the number of trials, the number of correct responses, the percentage of correct responses, the average reaction time, so the average time needed by a subject to answer on the interface, the total test duration, and the volume, which is the level set by the subject before taking the test. We have tested a machine learning approach in this study, a decision tree, to classify people into pass and fail, considering the slight mild level of the WHO classification. So from the audiogram, we've estimated the average pure threshold, PTA, pure tone average, and classified ears into pass and fail. And for the speech and noise test, we have extracted 8 features and used those features to classify into pass and fail. Before classification, we have characterized features. In this picture, you'll see the different distributions of features. On the diagonal, you'll see the univariate distribution of each of the 8 features, where the green subsample is the subsample of normal hearing subjects, and the red subsample is the subsample of subjects with mild or slight hearing loss, so above 25 dB hearing loss. We see that some of the bivariate scatter plots are quite interesting. For example, we see that the one involving age and SRT shows quite a nice difference in the two subsets distribution. The same holds for the SRT and reaction time, and the SRT and percentage of correct responses. In this study, we have used 2 different approaches. The first one, we used the whole set of features, and in the second one, a reduced set of features determined based on these pictures. So age, SRT, percentage of correct, and reaction time. With the 8 classification, we get to a decision tree, which is quite understandable and quite interesting. In the root node, we see that the first decision is taken based on the SRT, which is somehow expected. So depending if the SRT will be lower or higher than about minus 7.5, the subject will be classified as normal hearing and hearing loss, respectively. Then, in the right-hand side branch, we can see that age is also considered, and the number of correct responses, and again the SRT, and so on. That becomes quite a complex tree, but on average, we can see that the most important features, the most widely used features are SRT, age, and also reaction time, which appears down the tree. Regarding the 4 features, we select the one I mentioned before, so SRT, age, percentage of correct responses, and reaction time, average reaction time. This is the decision tree classification. Again, the SRT in the root node is the same cutoff, minus 7.5, and then age is used at the second level, and the average reaction time afterwards. Regarding the performance of both classifiers, we have compared the performance of the 8 features and the 4 features model, and also we have run 1,000 iterations to assess the variability of the model performance as a function of the specific data set. So in principle, we have split the training and test set using an 80-20% subdivision, and we have performed a 5-fold cross-validation in the training set only, so we haven't used the test set for cross-validation. Regarding the iterations, we have run 1,000 iterations by randomly changing the external splitting and the internal cross-validation splitting. So what we observe in the table is the performance of the optimal model with 8 features and 4 features, the one showed in the picture before, in terms of accuracy, area under the curve, sensitivity, and specificity. But the most important figures arise from the mean values obtained from the 1,000 iterations. So we can see that more or less the performance is exactly the same, whether we are using 8 features or 4 features. So we definitely tend to prefer the 4 features model, which is easier to understand, computationally more computationally cheaper, more understandable, and with the same performance as the 8 features model, with an accuracy of 77%, sensitivity 67%, and specificity of 82%, which are quite high indeed, because recall we are talking about speech and noise recognition versus pure tones. So the performance of the test is fully in line with that performance observed from widely used speech and noise tests in the literature. Regarding remote testing, we have used a volume control interface for the subject to adjust the level before taking the test, and we have compared the controlled in the lab with uncontrolled settings outcomes. We see that the SRT is not going to change substantially. We are obtaining the same SRT, whatever the settings, controlled or uncontrolled, so the SRT is reliable. Moreover, we have run an experimental characterization of transducers in a lab by measuring the real output level across the range of volumes used by the test using the same equipment, and by characterizing a large set of transducers, commercially available ones, from the cheapest to some more expensive. We have characterized them by measuring the real output level as a function of the volume level. What we have obtained is that, well, as expected, we have a large variability of output SPL as a function of the volume level set by the user. The bottom curves are related to the earphones, whether the upper curves are related to the headphones. We see that there can be substantial variations across models, across transducer models. So it is very important to introduce a volume control to compensate for the transducer characteristics. The blue line is the line of the fixed volume condition. The red line is the line of the adjusted volume condition. So we see that the subjects had a tendency to set slightly higher levels in the self-control condition. However, provided that we know the characteristics of the transducers, we can leave the subject with the flexibility to adjust the level. And this is really important for remote settings in order to have a real output level in the ears, which is a comfortable one and can be adjusted even by changing the transducer. So we wish the test to be used across different models in different ways. So briefly, the main outcomes of this study, we have demonstrated that the test can be valuable for multilingual settings. The performance did not change substantially across language. It is valuable for remote settings, for sub-screening, with increased repeatability, lower test duration, and lower influence of experimental settings compared to the conventional ones. A brief outline of our recent works that have led this outline presented in this talk, and some future research. Well, we want to test a large population, include a characterization of additional features, especially different machine learning algorithms. This is work in progress. We want to introduce automated compensation for ambient noise and developing the prototype app and testing. Particularly, we are looking for collaborations within the context of a new project, the WHISPER project, Widespread Hearing Impairment Screening and Prevention of Risk. So please feel free to contact me for any question and if you wish to collaborate. This is really easy and anybody can take the test and collaborate to this project and further developments. Thank you.
Assalamualaikum and hello everyone. My name is Nur Hafizah Muhammad. I'm from University Technology Brunei and I'm the author and presenter for the Dynamic Time Division Scheduling Protocol for Medical Application using Synchronization Algorithm paper. So as we all know that the wireless body sensor networks have become vast development in the application of internet artificial intelligence, and one of the application is the healthcare monitoring system. So the healthcare monitoring system will be able to provide sense data and alert any abnormality of the patient's health to the personal care, such as the caretaker or the emergency center. So in this application of the healthcare monitoring, it is very critical that the data are received simultaneously, processed and analyzed in order to diagnose the disease accurately. But there is also difficulty in receiving the data accurately. This is mainly because of the position, the position of the how the biosensors are attached to the body. This because the devices are attached at different part of the body, so the signals will be different in each of the devices. So since since the signals are different, so hence the signal or the sense data will not be able to synchronize and receive at accurate time. So hence in this paper, therefore we propose the time division based scheduling algorithm, where it can adapt and adjust its firing time according to the environment without affecting any sensing data, sequence, and the synchronized transmission. So in this this time division based scheduling algorithm is called the dynamic time division scheduling protocol. So this proposed algorithm can actually tolerate the single point of failure, where there is no centralized control on the transmission scheduling. So this proposed algorithm will be analyzed by using the hardware experimental testbed, and where the results were then compared between another two types of algorithms, which are the firefly synchronization fast and the default synchronization, which is the CSMA-CA protocol. So in this paper we'll show the comparison between the three, and it will show that the proposed algorithm, which is the DTDSP, will can adapt any network changes due to device addition and not removal or temporary anomaly due to the interference. So this proposed algorithm is based on the frog calling algorithm, where this TDSP allows the nodes fired evenly distributed within a time period. So this proposed will the frog calling the proposed algorithm will have show the equation 1 and 2 is the modified mathematical model of the frog calling algorithm. So where the epsilon is the one that responsible in distributing the firing time of the nodes, where the epsilon is the addition, the summation of between the two nodes, and then divide by 2, and then we multiply with the synchronization constant, where the synchronization constant is equals to 1 in this paper. So figure A, B, and C will show you the process of the proposed algorithm DTDSP, where figure A shows the initial stage before the algorithm starts, where all of the nodes seen are not in periodic manner and also not in the synchronized position. So it's all in random position. So when node A in figure B fired, it will look for the previous node, which is node B, and it will use the modified mathematical equation 1 to evaluate the new position. So as soon as node B jump to a new position, B dash from figure B also, the rest of the node will also repeat the same process, hence that each node will adjust. So all of the nodes will adjust its transmission position until all of the nodes are evenly spread within the length of period. So hence therefore the figure C shows you that all of the 5 nodes are evenly distributed. So that's the process of the proposed algorithm, DTDSP. So in evaluating the performance of the DDSP and the two other algorithm, so the experimental setup will be showing the will show the deployment of the nodes similar manner with the actual application of the healthcare monitoring system. As you can see, the diagram on the left side is the actual implementation of the node sensor nodes, where the sensor nodes are each of the sensor nodes have their own task, where it can detect ECG, body temperature, blood pressure, blood glucose, and so on. Okay, so in this experimental setup, we use the XM1000 as the biosensors and the Talos B as the hub, Talos B node as the hub or the gateway of the device. So the task of the Talos B node will be used as a monitoring base station to collect the synchronization statistics and monitor the scheduling of the data transmission. While for the XM1000 mode will be used as the individual sensor node that will collect the biodata to be transmitted within the clock cycle. So in this experimental setup, a different number of sensor nodes will be done. Were done, where the biosensors increase from 5, 10 to 15 nodes. So this three section will then be evaluated. And then the experiment will be analyzed the synchronization packet sequence and also the packet delivery rate, and these two types of performance matrices will then be compared again with the three types of algorithms, which are the DTSP, FAST, and also CSMA-CA. So in this experimental results, it will show you the sequencing of the packet delivered for 5 nodes for the 3 algorithm. And from here, it shows you that the DTSP transmission have broadcasted this data in a synchronous pattern. So basically, by observing or analyzing the data, we have analyzed the data for every 20 cycles, and it shows that the DTDSP 100% transmission of the nodes are synchronized, while for the fast it's only managed to synchronize 10%, and the CSMA-CA only managed to synchronize at 30%. So it shows that the DTSP in 5 nodes has transmitted the data 100% in a synchronized manner. So here is the statistical test for the 5 nodes, and this will show you the average of synchronization period for the individual nodes for each individual nodes. So again, if we observe this, it shows that the average cycle of individual nodes for the DTSP is very constant and very consistent. So it means that there is no delay or no traffic during the transmission packets to the base station. While for the fast, it shows that it keep on propagating. Still, the average cycle period are inconsistent. So it shows that the transmission packet were still propagating and trying to adapt the fast algorithm. So as the number of nodes increases to 10 nodes, the sequencing packet delivered, again, if we compare between the three figures, the DTDSP, it shows that the nodes were evenly distributed along the one period of time. So here, if you can see a period 4, it can show that all of the nodes are evenly spread in the period 4. Whereas for fast, it can be seen that it is still not in synchronized, and some of the nodes were double. And this is mainly because that one or two nodes were missing, so it tries to retransmit again the packets. Okay, again, by analyzing the data, the sequence data, it shows that the DDSP has achieved 100% synchronicity throughout the transmission, while FAST only achieved 10% synchronicity, and CSMA-CA only managed for 70%. Okay, so here is the average synchronization period for 10 nodes. Again, this is the average cycle period. So it shows that the DDSP is much more stable than the fast algorithm. So it can be seen that as the number increases, the average cycle for each individual are still consistent. And here is the sequencing of packet delivered for 15 nodes. So the number of nodes is now increased to 15 nodes. So this one, again, by comparing between the three algorithms, and when analyzing the 15 node sequencing packet for the three algorithm, so it shows that the DTDSP had achieved 65% synchronicity, while for fast it's can maintain only 15% synchronicity, and for CSMA it's 45% synchronicity respectively. So it is shown that the DTSP can avoid interference once the network has been synchronized. So any interference or any addition of the nodes, it can be seen that the DTSP shows a stable and consistent transmission of data. Even though that it shows that 65% synchronicity of the DTSP, so this is mainly because of the some of the one or two transmission was delayed. And this one shows the statistical task for the 15 nodes. So it shows that between the 3, 5, 10, and 15 nodes, so it shows that when the number of nodes increases to 15, the average transmission period for each node is not consistent for every cycle. In the three algorithm, especially fast, it's very hectic, the average cycle period compared to the DDSP. The DDSP, the average cycle is not far with the period given. The time period of the devices. So it also shows that the DTDSP is much more stable than the fast algorithm. So here it also shows the packet delivery rate of the three algorithms. So it shows that the DTDSP had a PDR of between 98.4% and 100%, while the fast PDR is roughly about 66.5% to 99.75%, and the random CSMA CA shows the PDR between 99.6% to 99.79%. So comparing between the three, it still shows that the DDSP has the higher average of PDR, even though when the number of increases, it still managed to maintain the average PDR between 100% to 99.6%. Is only like a small percent of error in the DDSP. So here is the scheduling effect during during network interference. So in this next experimental setup or testbed, it will show you the scheduling effect when a network when the sensor networks have some interference. So the interference basically from the battery when a node needs a battery replacement. So it means that the signal is lost for a few seconds or few minutes, and then it will go up again and continue for continuing the transmission. So that's one part of the scheduling effect. And the second part of the scheduling effect is when we add another one node into the system. So basically, when we added for the added node to the system, so it means that when that patient needs an extra reading or extra devices to detect the heart rate for extra information. So it will show you the scheduling effect, what happened when we added one or two or more nodes into the system. So here the scheduling effect, the first one is the scheduling effect during the network interference. This is where the battery replacement, what do you call that? The battery replacement, if there's any maintenance needed to be done. Okay, so this scheduling effect will show you between 5 nodes and the 10 nodes what happened to the synchronization effect, synchronization pattern. So in the first column, this is the DTDSP algorithm, and the second one is fast, and the third one will be the CSMA-CA. So it shows that so it is observed that during the initial time, they will show you the before node added, not added, and then all synchronized nodes. So between the three synchronization, the three algorithm between of the 5 and 10 nodes, it shows that the the DDSP shows it evenly distributed, and it's in a synchronized pattern. So it also shows that the DDSP maintain in synchronized pattern. Okay, so between the three, because when we see at fast, the time, the transmission pattern is still not it's in random and it's still inconsistent. Okay, so and then this is the scheduling effect of during the node addition. Again, it's still the same thing. It's between the three algorithm for 5 and 10 nodes. This is when we added one more node node addition into the system. So between the three algorithm, it shows that the DDSP maintain the synchronized pattern and still transmitting in a consistent way. Okay, so here is the conclusions. So it shows that the proposed algorithm has performed better than the CSMA and fast. The result proved that when a node needed for maintenance, the DSP managed to synchronize the packet data in a short time. So similarly, when there was addition of sensor nodes in the network, the algorithm can readjust its transmission interval. The proposed algorithm also able to synchronize the packet sequence and equally distributed and broadcast the time for the sensor nodes and is tolerant to failure. And the proposed algorithm also shows that this protocol will able to recover and continue to broadcast the data to the base station in a synchronized and in a consistent manners. So that's all for my presentation. Thank you for listening, and goodbye.
Good morning. I'm here to present a paper titled Has CoviHealth a pilot study with teenagers in schools of Central Portugal? In 2016, we have 340 million of persons aged between 5 and 19 years old, overweight or obese. Little known about nutrition and physical activity habits promote the decreasing consumption of fruits and increased consumption of candies and salt. The physical activity is decreasing with the age. Young people spend many hours of their day connected to a smartphone, which often leads to decrease in socialization. Hence, the idea of using smartphone as a means of education and encouraging physical activity and socialization. During the time of the study, different types of curiosity, challenge, and questionnaires were proposed to the participants in this study. The mobile application includes different methods to captivate the attention of the teenagers. It also includes methods to stimulate the physical activity. The gamification, personalized methods, and medical controls are some of the methodologies implemented. The teenagers answered different questionnaires about physical activity and nutrition during the study. The analysis of different answers was performed to evaluate the normal level of the teenagers.
Initially, a research about existing mobile applications in the market was performed with the following keywords, where 250 mobile applications were found in Google Play Store, where 73 mobile applications followed the defined criteria. The mobile applications are related to diet and nutrition, health, physical activity, and education that report features in the defined categories, such as anthropometric parameters, diet, medical parameters, physical activity, social, and vital parameters. We developed a mobile application to promote healthy physical activity and nutrition habits with 36 teenagers during 5 weeks, where by in the end of each week, the teenager fills a questionnaire related to types and curiosity present during each week. The mobile application has an initial questionnaire at the present 10 types, 18 curiosity, 4 weekly questionnaires, and 6 challenges. The teenagers were aged between 13 and 16 years old. There are students in the public school in the CoviHealth and Fundão municipalities in Portugal. Practice of the sport. 65% of analyzed teenagers practice sport. Only 62% and frequently the gymnasium or practice exercise during 1 or 2 hours of each day. In the sport players, 39% of the teenagers play football, 33% of teenagers play basketball, 35% of students prefer individual sport, and 31% of teenagers prefer team sports. In the diet, only 62% of teenagers are consuming 1 or 2 pieces of fruit per day. Only 4% are consuming candies between 5 to 6 times a week. And finally, 54% of teenagers are drinking only between half liter and 1 liter of water per day. In the questionnaires, 54% of the questionnaires are correct. In questionnaire 2, 40%. In questionnaire 3, 73%. And finally, in questionnaire 4, 54% of the answers in the questionnaires are correct. In feedback questionnaires, maintain the level of physical activity during the study, their food habits, and the use of questionnaires are merely useful to improvement of knowledge about education of nutrition and physical activity. Satisfied with monitoring of physical activity components of the mobile application, with the use of the training plan functionality. The use of types and curiosity are useful for most of the study. The use of gamification motivates the use of mobile application. Most of teenagers said that medical control is important, and the students' involvement in the study said that they will use the proposed mobile application. Comparing with the other studies, the improvement of the lifestyles and certification are not present in all studies, because it is not only related to the way and method to communicate and educate the teenagers for health, it is needed the adaptation of mobile application to the teenagers. The technology's equipment is a good manner to promote the good habits in different needs of teenagers. The technology allowed the healthcare professional to monitor the teenager anywhere. Different validate methods are important to cultivate the attention of teenagers, including the pedometer and the measurement of energy expended. The technologies cultivate this type of population. Thank you.
Hello, this is Pedro Moreno Sanchez from the Seinäjoki University of Applied Science in Finland. I'm going to present my research paper with the title Chronic Kidney Diseases, Early Diagnosis and Enhancing by Using Data Mining Classification and Feature Selection. First of all, this is a brief index about my presentation. So let's go ahead with the introduction. The chronic kidney disease is a worldwide current public health problem. In 2017, 1.2 million of people died from these diseases, and 10% of the population is affected by that. It doesn't present any symptoms at the earliest stage, but the point is that if the disease is diagnosed in the late stage, which implies a 19% of loss function of the kidney, well, it leads to hemodialysis or kidney transplantation in order to keep the patient alive. So all these things is translated into a premature mortality for the patients and a decline of their quality of life. So that's why it's so important to have a early CKD diagnosis for the patient's life in order to maintain their quality of life and expectancies of being alive. On the other hand, data mining, currently there is a lot of complex data generated by different healthcare stakeholders. So the data mining appeared years ago, and well, it has been used for developing computer-aided diagnosis, which is able or are able to diagnose complex health issues with a good accuracy and efficiency, and it's quite useful when the healthcare professional, the doctor, has no evidence available to determine which treatment is better among the others. So here in this work, we think that the data mining is useful to discover underlying chronic kidney disease patterns, because data mining will allow medical personnel in future, when this system or this algorithm will be applied in the clinical routine, to early discover those patients who are at risk of suffering CKD, and to trigger intervention with them in order to stop the advance of the diseases, and so to increase their life expectation. We have made a review of the state of the art regarding classification, data mining classification in chronic kidney disease. There are some studies that lack of results and reproducibility because they are using own data sets which are not public. So we cannot use those data sets in order to test our system on this data and compare the results with them. So that's why we have used the chronic kidney disease dataset provided by the University of California Irvine Machine Learning Repository, because we discovered discovered, or we noticed that there were quite a lot of studies that use these data sets with generally good results, as you can see, as the table shows. We have to say that the almost all of them use the cross-validation techniques in order to achieve their classification results. Some of them perform feature selection techniques, which are highlighted in blue in the slides, and you can see in parentheses how many features they will achieve for fitting into the final model. However, we detected that only one study, which is highlighted in green, use new data to test on the model. So they didn't use the cross-validation techniques, and they perform with the model new data in order to see how the model behaves with unseen data. In our research work, we have used the cross-industry standard process for data mining, which is a methodological way to manage data mining development, because it establishes a continuous loop composed by 6 steps, as you can see in the picture. So let's go with the first step, that is about business understanding. It's the most important because the intention of the project is outlined here. So what is our study goal or our research goal? Is to achieve a data mining model that guarantees a highly accurate and efficient classification of patients with chronic kidney disease. The next step, the data understanding phase, comprised to review the data that we are going to work on then. And in particular, in this research work, the data set, as I said before, was public and was taken from the repository of the UC University machine learning repository, and the data was collected from the Apollo Hospital in India during 2 months in 2015. It has a total of 400 samples, in which the ratio between patients with chronic kidney disease and patients with non-chronic disease is, as you can see in the slides. And we have to say that it has a one target feature, as you can see in the last row, and it has as well 11 numeric feature and 13 nominal feature. We have to say that all the features except the target class that are missing samples. Then the data preparation stage is really important for the system, because it is I'm at detecting data missing and to prepare the data in order to use with data mining algorithms. So here the missing value imputation, we have tackled the numerical feature data missing with a Bayesian algorithm as the mean and the median, and multi-variate imputation as a key nearest neighbor or iterative correlation. In the case of nominal feature, we have decided that the mode was the best technique to be used. Regarding the feature selections, it's true that relatively many features can overload the classifier, contributing negatively towards the calculation of the calculation, because removing some features can be considered unimportant and can mislead them. The performance of the algorithm is beneficial for the accuracy of them. So in this case, we have used the ANOVA for the numerical features and the chi-square for the nominal features, and the recursive features elimination and mutual information has been used for both type of feature, numerical or nominal. In the case of numerical features, we have used the min-max scaling in order to scaling the future with the aim that giving the model a normalized range of values among all the features. And in the case of nominal feature, we have encoding those values which are not numeric into numeric categories. In the case of the modeling phase, when the data is prepared for being processed, well, it's time to apply several classifiers in this case. We have chose these classifiers because they are the ones who have been used in the related works reviewed, and we want to know or to check our system development with these classifiers in order to compare our system with the related works. In the case of evaluation, well, splitting the training set is recommended in this phase to divide it into a training subset to decide which model performs better, and a validation subset in order to tweak the hyperparameter of the model to achieve better performance. The key fault cross-validation technique is the most appropriate to do this thing. However, the dataset should have been previously split to save a test set with the aim to run the model on unseen data. Thus, we can ensure that new samples will be classified by our system in the way that we experience with the training set. So here the ratio that we have decided to split the train and the test set has been the 7% for the training and 30% for the test. By speaking about the truly evaluation, we have used classification metrics as accuracy, precision, sensitivity, specificity, F1 score, and the area under the core rock. As well, we have used the confusion matrix in order to detect false positive or false negative in our classification tasks. Last phase is about deployment, and this stage is envisioned to put the selected model to perform new data in a product environment aligned with the project objectives. And concerning this research, in this phase, the model will be used in a clinical routine. So what has been which having the tools that we have used in this works? We have used Python as a language program with the scikit-learn library, and we have used the module of the library named grid search cross-validation, because it allows to combine multiple classifier, data missing imputation techniques, scaling and future selection techniques in order to find the best model to classify in our case the CKD patient. So speaking about the results, so you can see here in the picture our experimental setups in the right side, right hand side figure. You can see the different step of our data management pipeline developing this research that will allow us to find the best model to classify the patient. As a previous step, we have split the dataset into training and test set, as we have mentioned before. Next, when we have get the training set, we have split it in two branches, one for the numerical and another one for the nominal futures. Regarding the numerical, we have tackled the data machine, the future selection, and the future scaling by using the min-max, as we mentioned before. And regarding the nominal one, we have tackled as well the data machine. Before performing the future selection, we have to encode in the future by transforming the nominal future into numbers. Then when all this branch that concerns the pre-processing step has been carried out, the data has been fed into the classifiers in order to train and validate, and so to get the best model. In order to select the best model which performed the best classification, as I said before, the module grid search CV has been employed since it allows to find the best classifier applying cross-validation as well, trying a grid of parameters for every stage of the pipeline. The parameters are shown in the left side table, and finally the samples from the test set were used with the best model found to evaluate the classification performance with unseen data. And this last evaluation gives a real notion about the selected model for performance with new data. Here in the table, you can see the best combination of a classifier, data mission imputation, and feature selection. The best model with an accuracy by using the training set was the AdaBoost with the median and the recursive feature elimination technique. 4 for the nominal, 4 for the numerical, and 5 for the nominal, and you see that the results are perfect because we got 100% accuracy. In the right side, you can see a comparison of all the classifier techniques with the parameters of the best model. Then these tables shows the results that we got by using the test set. So as you can see in the upper table in the left side, you see that the best model that we got with the classification technique is not the best one with the test set. So this an overfitting episode happens because in some way the training features overfit the performance of the model. So we realized that the one of the 3 best model was the best one with the test set, as you can see in the table highlighted in blue is the 3rd row. Then looking at the confusion matrix, you see as the best model with the test set didn't have any false negative and false positive occurrence, which is a good point because if this system is going to be performed, is going to be used in the clinical routine with real patient, it's quite an advantage to not having false positives or false negatives. In the right hand side, you can see the different features and either nominal or numeric that were selected by our pipeline. Finally, as a discussion and conclusion, where we have developed a classifier model being used for early diagnosis of chronic kidney disease patient. The CRISP-DM has been adopted to ensure an appropriate methodology to develop a data mining system and a data processing stages. As well, we have decided to build a pipeline in order to automate the training and testing, and so to get which are the parameters of the best model. This pipeline will allow us to manage easily new incoming data. By using this this pipeline, we have get at the best model in classification of chronic kidney disease patient is the ADABUS classifier with a median technique with data missing for numerical features. The ANOVA with an amount of 7 features has been used for feature selection regarding numeric features, and the recursive feature elimination with an amount of 5 has been used for nominal features. Then we have to remark the train test split that we have decided to do here. We have get a perfect with a 100% accuracy, precision, and sensitivity in the results and in every classification metrics carried out. We have detected an overfitting case, and well, with these results, we have realized that, and we can ensure that the existing related works have been outperformed. As well, we have to remark the reduction of the features selected and how this has influenced into a good and better model from the state of the art. And last but not least, well, as a future work for this research, we would like to explore the future's importance of the system of the final feature selection in order to improve the interpretability of the model. Thanks everyone for the attention, and I will be glad to answer any question that you always. Thanks, and have a good day.
Hello, my name is Dino Mustafa, and I will be presenting the paper titled Cybersecurity Analysis for a Remote Drug Dosing and Adherence Monitoring System. This is the outline of the presentation. So first, I will present the motivation for this work, and then the challenges related to adherence. Followed that, I will present remote healthcare solutions, specifically adherence monitoring solutions. And then I will talk about cybersecurity and safety challenges. After that, I will talk about the proposed approach in the paper together with its application. And finally, we'll conclude the presentation with suggestions for future work. So why do we need remote healthcare solutions? Well, there are many reasons. Cost is one reason. Diagnosing patients at hospital is becoming costly. Treating infectious disease is risky for professionals. COVID-19 is a good example. And also, life expectancy keeps on growing, and hence populations aged 65 and above increasing, which needs a continuous follow-up for the elders aged above 65. And patients with chronic disease also require continuous follow-up, while working age population in healthcare domain is declining considerably, and hence there is a mismatch of patients to professionals needed. Therefore, all this leads to exploration of novel remote healthcare solutions for medication monitoring and treatment purposes. Why medication adherence is a challenge? Well, it is because up to 25 to 50% of the patients do not take their medication properly according to the prescription, and this non-adherence is cause for illness and failure of treatment. For example, patient relapse and hospitalization due to non-adherence, and also non-adherence can lead to higher rates of complications and even deaths. All this introduces additional cost, billions of dollars annually, due to additional treatment and hospitalization. Therefore, accurate assessment of medication adherence is very important. What are the status and the benefits of remote healthcare solutions? Remote care delivery solutions are growing due to a vast number of smart wearable sensors and intelligent handheld medication devices, as well as advanced connectivity technologies, both indoor short-range communication technologies like Zigbee or Bluetooth neurology, which are really good for power management, and also long-range communication technologies. For example, 5G is a good example, which will provide ultra-reliable, low-latency performance. So there are many communication technologies that contribute for growth of remote care delivery, and also there are many cloud technologies like cloud tools, integration tools, or machine learning algorithms that can be used as a part of a specific remote healthcare application. And the benefits are, well, many, to mention some. This will move hospital routines to home through personalized medication and remote adherence monitoring. It will enable massive data collection and hence analysis of diagnostic data through a smart algorithm like AI or machine learning, and hence improved decision by professionals, also improved service ultimately. And it will also enable saving both time and resources. It will reduce the time required for diagnosis and treatment. It will reduce the needs for hospitalization and emergency room visits. It will improve survival rate, especially in the case of rural areas. It will reduce costs both for patients and healthcare organizations. There are numerous healthcare solutions, specifically medication adherence monitoring solutions, which are, some of them are already on the market and some are on the process of certification. For example, medication event monitoring system is a popular application which provides very high standard information about adherence. There is also Acoustic, which is a diabetes care device connected with a mobile application for monitoring and treating insulin-dependent diabetes. There is also another technology from Proteus Discover, which is ingestible sensor. It's a sensor integrated in the medicine, and when the medication is ingested, a signal is relayed via a patch worn on the abdomen that links with a smartphone application and records that the medication was taken. There is also Ondosis device, which is a use case device in this paper, and it is a drug dosing machine with a remote medication adherence monitoring capability. All these solutions are connected to internet and hence are vulnerable to a potential cyber attack. Again, on doses, dosage manager, which is a use case, as I mentioned above, and the core features of this system is one, dosing medicine, specifically for patients with chronic disease, and also it enables remote medication adherence monitoring. The outcomes of the system are flexibility and precise dose adjustment for individualized treatment, real-time monitoring through integration of cellular technology like 5G. It will improve home care facilities, and it will reduce the number of patients treated in hospital. So in the picture we have connected IoT devices like the smartwatch tracks the body reaction, and the device with medicine, which sends all device events through BLE to the gateway device, and the patient reports symptoms using a mobile application, and all this creates IoT devices at home, and the data is collected using the 5G gateway device, and all collected data is then further pushed to cloud for further diagnostic data analysis by a smart algorithm which can help the doctors or can decide by itself the correct dose size that the patient has to take, and send setting information to the device, by which we create a closed loop medication management system. This closed loop management system can be vulnerable for potential attacks if we don't have a proper implementation, like the device can be attacked, or the connected IoT device can be attacked. Even the cloud platform can be attacked by adversaries. Usually the network interface is vulnerable for hackers or computer criminals. So what is the consequence if adversary actually alters the dose size? Well, overdose may lead to minor or permanent impairment, as well as death in some cases. Therefore, a comprehensive exploration of threats and mitigations are required to safeguard patients from risks related to cyber attack, specifically with this use case. So, cybersecurity is a practice of preventing unauthorized access and modification or destruction of a system, among others. So there are many threat agents that are trying to attack our systems, and they have different intentions. So, for example, computer criminals usually targets digital assets to disrupt service or manipulate settings, and their intention is getting money out of that. There is also insiders usually inject malicious code into softwares, and their intention is to espionage the company, which could be due to being fired from the company or other ill feelings. There are also terrorists which targets critical infrastructures to disrupt or to damage assets, mostly with intention of mass killing. So what are the potential consequences if actually a system attacked by these different threat agents? Well, data can be stolen, it can be a privacy issue, or it can be sensitive information related to the system. And also they could interrupt the service, which is mostly a serious case in time-critical applications. They could damage the system, and all these could lead to injury of a patient or loss of life in the case of medical domain. So safety can be defined as the freedom from acceptable risk of harm to humans, either directly or indirectly, as a result of damage to property or to the environment. There are mature functional safety standards for medical domain or medical devices, but if the medical devices are connected to internet, then the safety is not anymore guaranteed due to potential cyber attacks. So that's a challenge, and that need to be mitigated. There are no specific standards for medical devices as of now, so there are only best practices and guidelines. As an example, NIST cybersecurity framework can be used, and we used that in the process of devising our approach in this paper. FDA guidelines also can be used. There are many documents, draft documents and final documents, which can give guidelines on pre-market submission and post-market management of cybersecurity in medical devices. There are potential cybersecurity standards on progress and can be used in future for implementation of cybersecurity related to medical devices. So finally, the proposed approach, it is a top-down, step-by-step approach to investigate and analyze cybersecurity threats and vulnerabilities of a medical system. So the first step is identification step, where we identify all system components and the threat agents that give rise to threat and want to abuse the system, and all threats that are available out there. These threats can be looked into different databases that store different types of threats, and then we need to identify all vulnerabilities corresponding to the identified threats in our system. Once we finish that, we can move to the next step, which is the risk analysis step, where we determine the threat mode, which is a manner of fail of threat, and we determine a corresponding threat effect, and then followed by defining a severity matrix for our specific system. Similarly, we need to define a probability matrix for our specific system. And also we need to determine and define a risk criticality level matrix for our specific system. Once we did that, then we need to decide if risk is acceptable or not. If it's not acceptable, then we need to minimize the risk, so we need to implement countermeasures, and that will be the third step, or the mitigation step. So how to apply the approach in practice on a selected system? The approach can be listed as a series of process steps as shown in the figure and also listed here. So the first step is to identify all system components or all system assets. Followed that, we need to identify all threat modes for each assets. And then we determine the threat effects for identified threat modes, as well as determine the severity of each threat effect. Once we did that, we can identify the corresponding vulnerability in the system together with the adversary type that can potentially utilize or exploit the vulnerability. Once we identified those two components, then we can estimate the probability of a vulnerability being exploited by the threat agent. Followed that, we can determine the risk criticality, and if the risk criticality is not acceptable, then we can implement a countermeasure to minimize or to reduce the risk. This will repeated until all treat modes and then all assets are covered. So now we can implement the approach for the use case device that we have already described in the previous slides, which is the on-dosys device. So the first step is identifying the components of these closed loop systems. This can be some examples of the components in the system, and once we identified all the system components, then we can try to identify all threats out there that can potentially impact our system. Following that, we can identify the vulnerabilities that we have in our systems for the identified threats. We could identify also all threat agents that potentially impact our system. So this is the identification step. After that, we can go to step 2, which is the risk mitigation, the risk assessment and the risk mitigation steps. So we pick a component, one component out of the component lists, and we determine or we identify treat modes for that, all possible treat modes for that specific component. Followed that, we can identify or determine all treat effects corresponding to each treat modes. Once we did that, then we can map the treat effect to severity scales based on the seriousness of the treat effect, the consequence of the treat effect. And this is usually, or it is based on the severity matrix that we defined for our specific system. Similarly, we can determine or we can estimate the probability based on the vulnerability we have and the threat agent that potentially can exploit that specific vulnerability. So this completes the risk assessment step by estimating risk criticality from the severity and the probability. So once we determined or estimated the risk criticality, then we can go to the step 3, which is the mitigation step. If the risk is not acceptable, then it has to be mitigated, and hence we need a countermeasure implementation to reduce the risk related to a specific treat mode. So now we can go to illustrate the approach in the use case device. We can go step by step through the treat modes listed for the specific treat component, the system component that we highlighted here. So some of the treat modes related to this specific system component are here: spoofing, sniffing, jamming, and reputation. So we can pick one, that's spoofing, and it has a consequence which is incorrect. It can lead to incorrect diagnosis data, and then if this happens, then the severity is very high and it is catastrophic based on the definition for our use case device. Similarly, we can determine the the probability through if the vulnerability is obviously interceptable network, we have interceptable network in our system, and there are criminals or hackers that potentially hack our network, and this can be occasional because there are hackers out there, and if we have this device in a public, if we are using the device or the system in a public network, so the probability will be not negligible. It can be occasional, and it defined as two in our specific use case. Once we determine this probability, then we can estimate the risk criticality by multiplying actually 4 with 2. It gives us 8, and that number 8 in our risk criticality matrix gives rise to an acceptable risk. Hence, we need to implement a countermeasure, and the possible control can be encrypting data on transit. Similarly, we can pick the next threat mode, which is sniffing, and the consequence is information disclosure, which gives a severity of minor or 1. Similarly, we can calculate the probability, and according to our system, the probability is 2, and then this gives to a criticality of 2, which is acceptable according to our risk criticality matrix definitions. So if the risk is acceptable, we don't need to implement a countermeasure, hence this stops here without implementation of countermeasure. Similarly, we can pick the next threat mode, which is jamming, and the consequence is service interruption, and this can rise to a severity of 2, and the probability could be 3, because jamming is a common threat, and usually hackers jam a network just for the sake of interrupting a service, and it is a probable vulnerability that can be potentially exploited by threat agents. So serious or severity is 2 and probability is 3. When we multiply them, it gives 6 as a risk criticality, and which is defined as an acceptable risk for our system. And hence we need to implement a countermeasure, and the countermeasure could be a frequency hopping. So that concludes the application of the approach, and the conclusion is that the paper demonstrated the degree of cyber threats impact on medication and monitoring solutions. Hence, the approach to identify and analysis of threats and vulnerabilities followed by integration of controls is very important according to this paper. As a future work, one possible future work is expanding the approach so that the probability can be easily determined by non-cybersecurity specialists, like any medical specialist with any cybersecurity knowledge. So the probability can be estimated easily. So the approach can be expanded to include that scenario. Thank you for your attention. That's all about my presentation.
Good morning, good day, and good evening, everyone. We have participants from all world regions, and that was an additional challenge to organize this panel in the online format. My name is Mladen Vejinovic, and I am a full professor and dean at the Faculty of Informatics and Computing in Belgrade, Serbia. I would like to welcome you to the HealthyIoT 2020 conferences panel. Role of IT and IoT in responding to pandemic-related challenges, organized and sponsored by European Alliance for Innovation. The topic is obviously very important and very actual in this situation, and we have the honor to have amazing panelists. Let me first introduce Zona Kostic, who is a research, teaching, and innovation fellow at Harvard University. Kostic's recent advances focus on combining information visualization and machine learning into intelligent web systems, intensively collaborating with researchers inside and outside of the US. Hello, Zona. Today, we also have Professor Ivan Chorber, the Dean of the Faculty of Computer Science and Engineering in Skopje. Professor Chorber has an amazing record both in scientific research and industry. Our next panelist is Dr. Igor Kotsyuba from the National Academy of Science of Ukraine. Besides many other roles, Dr. Kotsyuba is the CEO and founder of HealthyIoT, a company that enables collaboration between hospitals and pharmaceutical companies on artificial intelligence projects. Finally, our fourth panelist is Professor Nuno Garcia from the Universidade de Beira Interior in Covilhã, Portugal. Among many other functions and roles, I think it is important to emphasize his leading role in an amazingly successful cost action about ambient assisting living and this chair role in last year's HealthyIoT conference. Dear colleagues, thank you for participating in this panel. It is my pleasure and privilege to have you here today. Ms. Zona Kostic, Professor Kostic, how can we facilitate the development of artificial intelligence in hospitals and clinical environments?
Ooh, that's a really tough one. So, I mean, first of all, thank you so much for having me here. It is a great pleasure to be with all of you here. When it comes to hospitals and when it comes to medical domain in general, this is not my own domain expertise, right? So my own expertise mostly is tied to education. But what we are trying to do is to actually bridge the education, what we actually call academia, with industry. So basically what we are struggling these days when it comes to medical domain is how to help our own students learn, giving this virtual environment, giving this new normal that we are facing here. So the basic question is, okay, we can extract data right now. This is a pretty big issue, but probably we can talk about it later on. We can extract data. We can use these data, but our own students also need to have access to it. What's going to be also even bigger issue is, if our own students have access to data and if they're capable of bringing certain results, would they be trusted? So we also know that medical experts these days, they trust themselves and their own colleagues, but there is a pretty big mistrust when it comes to any sort of, how can I put this, any sort of advanced tech and advanced automation that might come from research institutions. So I was I was part of the project with Harvard Institute of Applied Computational Science, in which we work with an AI project for medical experts only. And our task was to figure it out how we can bring trust, basically how we can increase trust with medical experts so they can start using medical applications. So these days we can use and scan MRI images and being able to easily figure it out who might have COVID and who might be a potential patient. But doctors these days have a really hard time to accept automation, ML boosted and AI boosted automation, even if the ML is working with much better accuracy. So this is what I see it as a pretty big problem right now, and I like to kind of jump with an issues rather than a potential, so we can maybe open a certain this discussion. Especially, I would like to probably hear from someone who might be an expert in the medical field, or actually working on the field, employing medical data in order to help fighting virus. I mean, if we have someone who is who works with implementing AI for a drug discovery, or someone who has any sort of information and close contacts to Pfizer, maybe, because they're the one who are coming up with vaccine.
Professor Czobe, Professor Kotsuba, what are your views on this?
It's true that it's difficult to get doctors on board and the trust towards automation when they are used to their ways and when they are focused on other issues, because their day-to-day activities don't involve as much innovation as we researchers in IT believe they do, because they are faced with day-to-day problems with their patients, with their medications they're giving, the effects of them, the stress and everything. They don't automatically see the results of automation, and it doesn't happen by itself. It doesn't happen tomorrow, so the effects are long-term. My experience is that certain more technically inclined doctors should be selected as proof of concepts, that those people are eager to embrace new technologies. And honestly, I don't think that the stress they are under now with the pandemic is the right time to show them something new, because their focus is elsewhere. Of course, if this automation provides instant help in this overstretched time, in this period where their strength and focus is overstretched, then they would probably accept it. But everything needs a learning curve, everything needs a period of adoption. And although the pandemic has been going on for a year probably now, we still haven't had the time to sit back and reflect on what we're doing wrong and maybe change, because everything is happening hectically quick. There was no time to sit back and reflect. Certainly, they have adopted telemedicine in a big way, because they try to avoid direct communication with patients. So although telemedicine has been here for ages, for decades, they are only now increasingly adopting it in an effort to preserve their health and not to spread the virus in hospital waiting rooms. So this is a big chance for telemedicine to re-emerge, because it was somehow forgotten.
Thank you. What is your view on this?
Yeah, I completely agree with Zona and Ivan. First of all, Zona mentioned that Trust basically, let's visualize. I mean, this is a mountain, the hardest mountain in cybersecurity and IoT domain to climb. And in healthcare, it's specifically difficult just because healthcare sector and pharmaceutical companies, all of them are quite conservative. They understand that data is their gold. And on the other side, they're obliged to be in compliance with all the regulations. And regulations are basically stricter and stricter. And so that's what we basically do in this our spin out company HealthyIoT. So like we work in healthcare for anonymity of data, right? And so we try to use federated learning as quite promising direction for this. And so basically we understand that IoT is not about devices connected to network. It's all about the multimodal data coming from different sources, and we understand that there is large amount of this multimodal data. So what we want to do is to fuse this data to provide clinicians, clinical research organizations, pharmaceutical companies, all the stakeholders with real tool how to exchange the data with respect to all the regulations, and how to basically have this data fused, which means we utilize all the powerful things of IoT. So that's my view on this particular question.
Thank you, Professor Garcia. By talking on this panel, you shared some great insights on the relationship between society and technology. What are your views on the current situation and the future?
And first and foremost, thank you so much for the so kind introduction. It's a pleasure to see all of you again and to be in the company of such great scientists and friends. So, in fact, I think that your question to me is also a little bit related with the topics that Zona, Ivan, and Igor have been discussing. So, Zona was talking about the difficulty of imposing trust, or not imposing, but allowing the growth of trust in the medical area. And Ivan and Igor also mentioned this. So we have a problem here, and the problem is that in our society, everything is pretty much made of balances. So companies and science, they establish themselves, and they are kind of in a balanced state where all the pros and cons kind of align themselves, and there's hopefully a positive outcome of that. But the thing is that computer science is much faster than our traditional science areas such as medicine. So what we can see here is that we are working in a pace in which they cannot. It's impossible. It's humanly impossible to cope with the discoveries that we make every day. The other day, I was talking with a friend, and he said that the first medical area that would disappear because of computer science would be imagiologists, because they just analyze the result of CT scans and X-rays and so on. And nowadays, computers do this much better than trained professionals. I'm not so sure about this, but I'm very, very sure that if I was in a position where I would have to rely on a diagnosis for a imagiologist, I would like to have the expert opinion of an expert system with my data. So the question related to what is society going to do with this, it's not really an easy question at all, because on our side, from computer scientists' side, we are trying to push the medicine area and the healthcare area way too far and way too fast that they are allowed to go. And this, of course, creates the difficulty for trust that Zona was mentioning, and also creates the problems with anonymity of data and so on that Igor was also mentioning. I guess that we are in a pace where we make so much science and so quickly that we will lose many important scientific discoveries in the process. I would like to have, for the sake of keeping the balance between things, I would like to see a more integrated approach to these new discoveries in computer science and in medicine. And this, of course, I think can be made of building trust between each other. Only recently I have seen medical doctors and experts coming together and working with and looking for computer scientists to kind of enhance their own areas. So I would like to see a more transversal approach to knowledge that integrates computer scientists, scientists from medicine, scientists from pharmacology, and so on. I think this is the only way where we can build sustainable knowledge and sustainable science that can actually lead to usable and trustable solutions for everybody. Yeah, I think I would just leave it at this point.
Can I just follow up shortly? Because there's so many things that you tackled, and especially this one, the last one was the most important, is gathering experts from many different fields in order to come up with better solutions. And so this is towards creating AI and towards creating automation that could not replace us one day, but work in collaboration with our own domain experts. And I think this is the actual trend that I'm seeing right now. And it's the trend that I can see as part of the research institutions. And I'm pretty sure it happens in industry too, because we have pretty good ties with industry over here. So I've read about a research where AI was implemented specifically for medical domain, and the accuracy of this algorithm was around 95%. It kind of beat all of the doctors. The accuracy of doctors was 92%. But when they started working, when they were when they went through the entire test in collaboration, doctor as well as AI tool, the accuracy was 99%. And this is the actual trend. So, and there are so many projects these days in which you can see that we are using data visualization, for example, for completely new field called explainable AI, because we as AI experts, we don't understand how automation works every single time. So we need some sort of an eye through, some sort of a magnifier of a certain stage of the automation. And we have data visualization to help us learn how AI thinks, but we also use visualization to give feedback to the AI. So it will be great. I would really like to see this one day. It will be great to have domain experts, medical experts working with AI, being capable to enter this human in the loop. When they can give feedback, AI can actually learn from domain experts, but the end decision will always be on a domain expert. It will always be on a medical expert. And then Igor, I believe he mentioned great things such as using federated learning, because this is one of the other constraints that we have in this entire field. So not only that we need more data to better train our own algorithms, but we need to make sure that we are keeping our data safe, right? So how we are going to how we are going to be creative and responsible scientists within these two constraints. So this is what I'm actually thinking about constantly. Thank you so much.
Thank you.
Yes, I would just like to add one more comment. I would like to agree completely with what Nuno mentioned at the end, especially, of course, Zora as well, because especially the part where two domains need to get close to each other and exchange opinions and build trust amongst each other, because IT experts and doctors need to much more often, because we do reach both groups, but very often detached from each other. And we think we are doing the right thing, and when doctors look at it, they don't understand it or they don't approve it. Or on the other hand, when we see doctors doing something, we say this can be done much faster and more accurately with an algorithm or with a computer. So we need more of that. We just ended a cost action called Open Multimed, which was focused on systems medicine and multifaceted, multi-dimensional machine learning in the medical domain. And there I noticed that we live in two separate worlds. IT people and doctors, we live in separate, water balloons.
The languages are different. We speak different languages. Yeah.
Right. Different terms for the same thing. So we need this collaboration to intensify to get the results. And we must also mention that the biggest advances in the medical domain in the past probably 30, 50 years have been thanks to science and technology and computer science as well. Not only analyzing data, but data generation. You mentioned radiologists and images. Not only processing the made images is better sometimes by computers rather than humans, but the generation of those images themselves. Now they have 3D models of the colon with CT scans instead of actually having a colonoscopy. So those 3D models didn't come by themselves. Computer programmers made those 3D models out of 2D slices of CT scans. So advances have been made, most of the advances have been made thanks to science and technology, computer science probably mainly. So we should promote this and get people to collaborate much more. Thank you.
Okay, thank you. Professor Garcia, how can we use large amounts of multimodal data from electronic health records, cameras, and medical devices to develop artificial intelligence systems?
Okay, yeah. We tend to think that most of our AI models need to use a lot of data, and usually that's the way it goes, although there are some new models, and I'm sure that Zona may be more authorized to talk about this than myself. But we do need a lot of data to do things. And I would like to point, not trying to escape from your question, but I'd like to point something that is, we have been discussing the use of data and the use of technologies to diagnose and to help doctors while diagnosing. And I truly think that the future is going to be something like this. We will have machines and sensors that will provide us a lot of data. We will be able to use this data alongside with expert algorithms and the opinions of medical staff to process that data. But we will use that data not just only for diagnose, but also for prediction. And this is where I think computer scientists can bring the edge towards medicine, because in the most cases, when we attend to a medical appointment, what we are looking for is for some kind of diagnosis. So when we reach the medical appointment, there's already something not working well with our systems. Let's use some kind of computer science language here, because I think it can be more easy for me to explain this. So we only go to see the technician after some alarms have been risen in our system. So I think that large amounts of data will be collected by novel devices that will collect data from our bodies and from our environments and so on, not just on ourselves, but the temperature in the rooms and the quality of the air and maybe radiation, maybe exposure to the sun. I'm not sure if you have heard that it seems that people who have vitamin D deficiency are more exposed to this new virus than the other persons. So I'm guessing that new devices sensing more things, collecting more data alongside with novel algorithms will help us to not diagnose, but before that, to predict and to help us orient our own behaviors as to prevent us from being sick. We have two very interesting results of our own research here at the assisted living laboratory at the University of Interior. One of them, and I'm sorry to I'll be quick on this one. So one of them is on predicting when a diabetic person is going to have an hypoglycemia crisis. So this is, of course, is quite easy to do if you have an inside body a glucose pump, not glucose pump. Sorry, I always forget the name of the hormone that diabetics use. I'm sorry for this. So this is where you can see I'm not a doctor. Well, I'm a doctor, but not a medical doctor. Okay. Insulin pump. Okay. So if you have an insulin measurement inside your body, you can detect if the levels of glucose are going too low or too high, and then you can correct that. But what we have done is we have collected measurements from regular diabetic patients, the one that use the finger prick to measure the glucose levels. And we have merged that data with data from lifestyle, exercise, meals, biometric data. And we have been able to predict almost 90% of the times when a person is going to have an hypoglycemia crisis in the next 24 hours. So thank God I'm not a diabetic, but I think that diabetic persons do understand, and they know that if they follow a given lifestyle, they are more prone to have an hypoglycemia crisis than if they follow other styles. So this is, I think, this is a very early result, but it's a very, very important result, because this is something that really helps you and prevents you from having, for example, a serious accident while driving a car and passing out because you have an hypoglycemia crisis. So another result we had in a completely different area was when we processed signals from intensive care unit patients. And to be quite frankly, the only thing we measured for patients that were interned because of a heart condition was the variability of the heart rate. So ICU patients, they are constantly monitored, and we measured the variability of the heart rate during a given interval. We have been able to predict if the person was being discharged or, on the other hand, would die in 85% of the cases. Just because we found out that, and of course this is a well-known result, we found out that the degree of self-similarity of the heart rate signals decreases sharply before the person dies. So this is the kind of metrics that usually devices on ICU units, intensive care units, don't show to the doctor. So we are not really sure on what is the real impact of this kind of result on therapeutics. But I think there is a huge field where we can get data, merge data, experiment, and bring to the attention of the medical area. Listen, why don't you try and see this? Maybe this is something that you should consider including in your scores. And I'm not sure, I've talked too much already. I'm not sure if I responded to your question. But for me, that is the future. That is new devices, lots of data, new algorithms, and prediction. Yeah, much
True.
better.
And I would like to follow up, because as soon as you mention multimodal data for AI expert, is like putting us in a candy store. Definitely, just give us as many data as possible until we get sick of all of these candies, because we don't have time to actually process them all. And it's great, unlike as I was talking about, having this cohabitation between domain experts as well as AI. It is great to see all of the tech and applications that are going to help us as users figuring out things when we are on our own. Unlike the application that was just mentioned, there is, I believe, the entire field of AI called assistive AI, specifically for people who live in suburbs, because we have a lot of people who live in remote villages or remote cities over here, and they usually live on their own. There are systems right now, embedded cameras, that are gonna track them and figure it out. If something happens, they're gonna call for help. But unlike that, or just on a side of this, having sensors to monitor health stage and health state of this potential patient would be also crucial. And these are tons of data that we can use, not only to understand how patient feels, but as Nuno mentioned, we can also understand, is there any potential danger that comes our own way. We can predict, something is wrong with this person, maybe we should send help ahead of time and be able to actually do something. There is one more app that I saw recently, and it was kind of on a funny side, but it's not really funny. It's actually really, really useful, and it's really related to COVID. So it's a cell phone based app in which users, just when they decide to leave a house, they can just switch it on. They can put headphones, and the app will actually measure. The app will actually listen others and figure it out based on the type of coughing. Is this person have a COVID or not? So you can kind of distance yourself. And the application is actually looking for more and more coughing examples, so they can come up with better results. And they're promising and trying to explain that by donating your coughing sample, we're not going to know who you are. We're not going to violate your own privacy, but it's going to help us, as well as it's going to help you as a user to accurately understand what's going on in your own environment.
Thank you, Susanna. Dr. Kutsuba, your company, HealthyIoT, was incorporated to provide a platform for collaboration between medicine-related institutions and artificial intelligence. How do you see this?
Basically, all of us, we understand that AI trained on limited data set, basically it's worse scenario, let's say. So AI trained on good data set, yes, this AI can help us. So that's a problem, because sometimes models are trained on limited data set, and then it's distracting in clinical environment. So what stakeholders need? I mean, doctors need something useful, data is fused, the situation awareness or decision support system has fused all the data. I mean, CCTV camera tracks the eyes of doctor. The other cameras just analyze either this is blood or not blood. And so it can create really useful tool for clinicians. So that's what we are working on. And again, so federated learning can easily enable exchange of these data. Just because of the privacy concerns, AI is it's very difficult to implement this in clinical environment. And again, the sector and hospitals are not really open to collaborate all the time. I mean, when we do research projects, because we participate in Horizon 2020 and a lot of them on healthcare. And so basically, sometimes we need to really have normal friendship with hospital to get this data, even if it's legal. Because hospitals, even if there is a legal framework how to exchange the data, they try not to do this. They try to avoid this. And we as researchers, we need the data, right? AI as a model needs the data to be trained on. So we try to tackle all these quite difficult problems. But I believe that's all about the awareness. It's all about the development of our own computer science products, right, to be presented to clinicians.
Thank you. Professor Chorber, we've seen several IoT architectures ideas to battle virus spreading. What do you think about the possibilities, realities, and privacy?
Thank you. Well, ever since Pele, the cost action, we analyzed a lot of IoT systems to monitor elderly at home, to try to help disabled people, to monitor their well-being, to alert someone if they fall or don't wake up in the morning or whatever. So similar experiences I have thought of using those experiences into a complex architecture to monitor COVID patients and possible spread of COVID patients. A really serious architecture would be almost impossible to be made, because that would include thermo-infrared sensors in hallways, malls, airports, in buses, in metro stations, all over the place. Besides those infrared thermal monitors, you would need cameras for facial recognition, probably, which also borderlines terrorist security research that had been done after 2001. Those cameras that detect stress in the lines in airports, or they detect anxiety amongst airline passengers. So you would need a lot of sensors, infrared thermal sensors, facial recognition, of course, cough detection, and then you would need to aggregate all this data, which would mean a lot of data traffic, and that would mean a lot of data storage, and then data processing. So I guess you would need to detect suspicious people that have increased temperature or cough or facial expressions, and then match them to the identity of the patient and try to alert this person into getting a test and going to be isolated for a while. This is huge intrusion of privacy. So this would mean Big Daddy big time. This would mean constant monitor of everyone everywhere, which is a real issue, because this can be misused very, very easily, very, very quickly. The price of this would be huge, the cost to implement it, and then so I guess the route taken should be somewhere in the middle of the road. We do need some infrared sensors on busy places. We need infrared sensors on places where people frequent, and when people enter closed rooms, now especially in winter, when no one will be staying outside, but everyone will be inside not really well aired places. We should have some kind of constant monitoring and detection of suspicious situations like increased temperature or cough, to try to alert everyone into some action, like taking someone outside, getting a test or something. Also, smartphones. Here in Macedonia, we developed, not we, a company developed an app that was promoted by the government in the cell phone, where everyone can carry it all the time, and the application monitors how close you get to other people carrying the same application on their smartphones. And then if someone gets diagnosed, they look into backlogs. If two people have been near each other a couple of days ago and one of them is diagnosed, then the other one should get tested or something. But the application drains your battery quite significantly, and I don't think many people use it. I tried to use it for a while. It was draining my battery, and if no one else is using it, then there's no benefit to it, because the data from your movement around cannot be matched to other people's movement. So we need architectures, but we also need control of data privacy, and also control of who uses the app or who doesn't, and does anyone actually use it. So architecture will be complex, big, expensive, or moderately placed in significant places like crowded corridors, entrances into public buildings, and at least some basic detection of fever or coughs or other symptoms that can be easily detected. I was thinking along those lines.
Thank you. Professor Kostic, if they're able to access this type of data, would they be able to provide medical experts with valuable insight? How is the collaboration implemented in practice?
Okay. Usually with talking to and collaborating with industry. That's for sure. And luckily, there is something that exists with American educational institutions that I haven't seen in Europe yet, and I hope to be able to see it soon. It's something that we called capstone course, and usually capstone courses are introduced as part of the graduate school at the end of the school period. So, for example, student can choose to write a graduate thesis, or he or she can choose to go for capstone course. And more students, which I'm really glad, are actually choosing to go for a capstone course, because capstones are one semester long project-based learning, in which we gather students in small teams, three to 5 maximum, and they have to work on certain problem for a company that we call an industry partner. And it's a great opportunity for students to actually help medical workers these days, medical experts. It's also a great opportunity for medical experts to delegate some kind of work, some portion of their own work to our own students. And what is a great benefit on it, and of course school has its own benefit, because the school can say that we have a great partners. You know, we have MGH as a partner, which is one of the greatest hospital in the entire US. Unlike medical institutions, there are partners such as Google, Facebook. So, you know, institution can say, okay, we have a great partners, which means we work on a great project. The most interesting thing, just not to deviate from the topic too much, is that the project of this kind, which is usually code, which is usually AI algorithm, belongs to students. And then students have this opportunity to choose, are we gonna come up with a publication and just give the code to everyone, or we're just going to give it to our own partner, or we're going to ask partner for some sort of compensation, maybe for not necessarily monetary compensation, but we can ask for an internship, or there are so many different ways, so many different opportunities that could take place right after this, right after the capstone course. But I'm seeing capstone courses basically as the best possible way to help students getting closer towards the domain issues that exist. And just to basically shortly follow up with Ivan, and both Igor and Ivan, it seems that an issue here is twofold. So we do have data, and we do have a lot of data, but there is a kind of a risk that we're going to expose our own users. For example, I also read about the application in which it was recommended, if you plan to go to the office and work from the office, use this app where you can track every other person who is in the same building as you are, which is kind of dangerous. I know who's going to visit a restroom or something similar. But then on the other side, there is still not only a lack of trust, but Igor also mentioned that medical experts, even when they can, they are not giving this data to us. So even if we have data, we are creating algorithms that medical experts do not trust, or we have a second issue that medical experts are not giving us sufficient information, or a third issue that we are kind of we're actually telling, we talk about users and we are revealing some vulnerable information over here. So I think that there are so many constraints that we have to take into an account.
Thank you, Professor Kostic. Professor Chorbe, about distance learning, because of the pandemic, what have we learned? What are your experiences?
Well, overnight, the entire world probably turned from traditional classrooms into distance learning. And of course, giving a lecture in a classroom is nothing like distance learning. Everyone had to go through a crash course of distance learning techniques. No one offered any distance learning crash courses, so it was learning by trying with trial and error. We've accomplished many things, but exams remain the most complicated thing to perform, to have a trustworthy, reliable evaluation of the student's knowledge. What we have learned probably is that in distance learning, you have to have much more effort to get some interaction. You need much more interesting slides with much more dynamics to get people to attend your lecture and to focus, because it can get quite boring quite quickly and people can get asleep when they listen to your lecture in the bed. So we need much more dynamic, much more interesting lectures that last shorter periods of time. And the exams are, for me, the biggest challenge, because you need monitoring of your students while taking the exams, which takes a lot of time and effort. And then the results are not generally 100% sure, definite, certain. But anyhow, it's much better, and we've advanced a lot. And I think that some of the things we've achieved during distance learning because of the pandemic will remain afterwards. For instance, if you miss a class because of a business trip next year, you will not be substituted by a friend, or you will not be making a double lecture when you come back from your trip, but you will probably offer them a distance learning lecture after at the exact time when you should have taken your lecture, although you are 1,000 miles away on a business trip. And also, the video content we've created should probably remain there for students to revisit afterwards and reuse it for learning when they feel like it. The main goal is not to fail students. The main goal is not to evaluate, but the main goal is to teach them. The main goal is to get them to get more knowledge. So although the most complicated thing for me is the evaluation, I don't really care much about that. The main thing is for students to learn more. And we need a lot more learning about distance education, because now we are transferring this knowledge to primary and high school teachers here, and they're not ready. They're not proficient enough with computers to be able to properly teach remotely. Because when we started teaching, we are a computer science faculty, and people understand teleconferences, people understand presentations and everything. But when you include non-IT teachers into distance learning, it gets a bit more difficult for them, because they don't work with computers so easily. So it's challenging, but it it quickly brought us, I don't know, 20 years later, it forced us to do distance learning, although we didn't feel ready for it, or we didn't feel it's the time to do it. We were quickly brought to a distance learning situation that we didn't prepare for.
Thank you. Thank you. Professor Garcia, how your university reacted to the pandemic? How your students and learning process were affected?
That's a very interesting question, and I think that we can only truly respond to that after some time, because you put the tonic on how are the students responding, and I think that Ivan provided a very good perspective on what was the problems associated with the professors and the faculties and so on. But the thing is that the students, they did not enroll in university to have this kind of classes. So many of them are feeling that the university has let them down. So when the first lockdown of the epidemic occurred here in Portugal in early March, I received tens of emails of students saying, please call us, we will go to the classes no matter what, because we cannot stay at home. Either we don't have the means, or we don't have the internet, or we don't have the computer or something. They really wanted this to be as normal as possible, as fast as possible. And of course, we know now that this was not to happen, and it will not happen for some time now. And the thing is that we are here again on the game that is to rebalance, to recreate the equilibrium of the learning teaching process. And of course, there are two very different radical points of view. One of them says, yeah, of course, this is not the same thing, but everybody takes courses on Coursera and on, then lots of big faculties in universities are promoting online study. So this is going to be the future. You might as well get used to it and get done with it, and that's it. And of course, there are some people who say, yes, it's true, but things will never be the same as with presential learning, and you will definitely need the presence of a skilled professor to convey you all the knowledge that she has to give you. And I think that both of these perspectives, they are, although radical, they are probably both right. The future will not be the same here. Students will definitely not be the same here. I was commenting to a friend a couple of days ago that there's a whole generation of students who lost summertime romance. Didn't go to the beach and had the opportunity of interacting with each other. So all of that is lost. And what will be the impact on students, on personalities, we don't know. Yeah, we can only hope that our resilience, that is so characteristic of humans, will help us to overcome this whole lost year. It's going to be a whole lost year in the best of cases. So regarding our faculty, what we did was, in a very early stage, we completely locked down the whole country, including, of course, the faculty, and that remained as such. And I think until, I don't know, maybe April or May, it was a large period of time. And then classes remained virtual, online, exams online. And recently, the higher education minister and the government ordered us to go back to classes and teach as if nothing happened. Of course, keeping social distancing, keeping measurements that were declared by the general direction of health. And what has happened is that, of course, things have been done like that. There are only a few cases of contamination among professors. There are some 30 students who have been contaminated, but given the overall scenario, this is not so bad as we could expect. So I guess we kind of coped in the best of ways with the difficulties, despite the fact that, for example, the second and the third years of computer science in my department, because there was a few students that were infected, they are all having their classes in a remote manner. But the effect of this on students, we will never know.
I need to follow up shortly with the summertime romance, and I'm not going to take too much time because I know that we are approaching towards the end, and this is something that is definitely tied to European schools. So it's like children really like consider going and studying in Europe. Yes, United States has a great educational system, but here students are coming to colleges primarily to obtain, how can I put this, more social contacts. Basically, they're coming for socializing first. Of course, they're great experts here, but contacts that they come up with are staying for lives, because students are pretty, let's say we're having pretty good students, right? So they're gonna reach some level of either someone is gonna come up with a startup company, someone will end up working for Google, Facebook. So if we just think about like, where is my friend from a first year? Where are my freshman friends? So these connections are staying for life. Canceling that was a pretty big issue here. So this is why everybody stopped working and everybody are banned to go and visit campus since March. I haven't actually visited my own campus for how many, like 6 or 7, 8 months right now, except freshmen. So newcomers, they are staying here. So we basically emptied everything so they can enjoy this beautiful, special experience that they can only have when they're freshmen. Okay, I'm not talking anymore.
Thank you, Susanna. Since we are almost out of the time, what would be your final remark? Maybe Dr. Kotsuba, if you have.
Just final remark. It's the whole world is suffering from all this, right? So the doctors basically, they don't want to see patients in their rooms. And by the way, as a company, HealthyIoT, so we were approached like by one huge cosmetics and beauty company. The company works in beauty domain. So they approached us for developing the AI platform to have clinical trials for cosmetics. So first of all, we were shocked that cosmetics has clinical trials. And second shock was they want platform with AI to have this clinical trial at home approach in cosmetics. So we are still, we're working on this idea. And European Commission also had a few projects we were participating in on clinical trials at home. So for sure, world has been changed since COVID, and we need to have these digital platforms, digital instruments, digital principles with respect to all the regulations. Maybe somehow we need to change regulations, of course, but anyway, this is a great time. Again, for instance, about data sets, probably we need to create synthetic data set and meet next pandemic with the synthetic data set as a scientist and just tackle it easily, like let's do it in a 3 weeks period, not a year. For Pfizer to succeed. So I believe that as scientists, as computer scientists, we are doing a great job, and let's rock further, in this case.
Thank you, Professor Kotsuba. Professor Chorbe, final remark.
Thank you. It was a real honor to be amongst the great people this afternoon. I have heard things that will remain with me for ever, as long as I live, won't be forever. I feel disappointed about how the world faced the pandemic. Honestly, we thought we live in a very advanced learn, but generally the approaches were medieval. The quarantine is a medieval approach, and the shortage of facial masks, hand gloves was preposterous, even in the most developed of countries. So I agree that we should prepare to face the next pandemic much more prepared, for vaccines to be able to be created within a couple of weeks, couple of months, not a couple of years. Of course, computer science can help with most of it. Artificial data set was a really good idea, and because we can simulate different diseases differently, and we can activate the data set most appropriate to the new disease when it emerges. So I agree completely on that. We learned a lot of lessons, and we should be more prepared next time. Of course, we should finish with this time first.
Thank you. Thank you. Professor Garcia, your final remark.
I'm still making notes of what everybody has said, of course.
Okay.
Yeah, it is a true privilege to be with you guys. Thank you so much for the invitation. Final remarks. There is a long, long way ahead of us. We have come a long way since the early days of, well, my first microprocessor was the Intel 8088, so it was an 8-bit processor. You can see how long I've come. And of course, Professor Mladen can relate to this. We are probably two of the most senior participants in this meeting. Yeah, in the early days, computer science was not at all like this, and we were very, very happy. I was very, very happy when I could simulate a pseudo-random number, extracting random certain parts of a sine calculation. So we have come a long way. This is true, but we have a very long, long way ahead. We have a very long road ahead. The beauty of it, I think, is that computer science is not just only for scientists, although, of course, we are responsible to drive it. But computer science is nowadays a commodity in the hands of everyone. And this brings us new challenges, new problems, including, for example, anonymization of data. But of course, it makes it so much more interesting. And I think that in the future, we will be able to see us as computer scientists to contribute in a very positive manner to all these challenges that are going to be coming up in the world. And I'm really, what can I say? I'm really looking forward to design a part of this future with, of course, with you guys, if possible, because you're my friends. So yeah, this is what I would like to do. Thank you so much for the opportunity.
Thank you, Professor Garcia. Professor Kostic, your final remark.
Well, since the understanding is the essence of everything, I would like to see more panels, such as this one, being organized so we can meet, talk, and learn from each other in order to go towards speaking the same language one day. I mean, we are at home, so what else we can do? Thank you so much once again.
Thank you, dear panelists. Thank you for being here today. I'm sure our audience will benefit from the insights you expressed here today. Have a great day. Have a great evening. Thank you once again.
Thank you.
Hi everyone, this is Danson. On behalf of my colleagues, I am presenting the paper Interpreting the Visual Acuity of the Human Eye with Wearable EEG Device and SSVEP for the 7th EAI International Conference on IoT Technologies for Healthcare. In this presentation, I will be discussing a few things as shown on the outline. First, I will provide some introduction and background for the work. Then I will explain what ionography is and provide two approaches, a hardware-based and a software-based. Next, I will talk about the signal processing algorithms used in the research to obtain the resulting SSVEP visual field representation. Then I will talk about the procedures and the results of the hardware and software ionograph experiments. Lastly, I will discuss the findings, conclude the research, and provide possible future directions. Wearable technology has enabled the quantified self-movement to transform from a cultural phenomenon into an essential lifestyle. The ability to self-track and log various aspects of one's life leads to cheaper and more accessible means of personalized health and wellness care. Wearable EEG devices can be used to track user sleep patterns, mental state, and cognitive health. The collected EEG data can provide immediate feedback to the user about the possible behavioral changes to improve the user's mental health and wellness. This paper extends from this idea of cognitive health tracking and considers how humans can use a wearable EEG device as a reliable and accessible eye health monitoring device. The novel method uses steady-state visually evoked potential responses to visualize and quantify the visual acuity of the human eye. Visual acuity refers to how well the human eyes can precisely acquire details at a distance. Deficiencies in visual acuity have been shown to significantly reduce a person's quality of life. This paper investigates how a wearable EEG device and a visual activity measurement technique known as SSVEP can provide an insight into the visual acuity of the human eye, and hence the visual perception. Essentially, this study aims to quantify and perceive how the human eye sees. SSVEP responses are periodic responses evoked by a visual stimulus flickering at a specific frequency range, from 1 Hz to 90 Hz. These responses oscillate at the same frequency as the flickering stimulus and are detected using either EEG or fMRI by measuring brain activation in the visual cortex. In the figure shown, EEG data from the OZ location, graphed in the frequency domain, displays SSVEP response at 8.5 Hz. The human eye can see objects that emit and reflect light. The distance, spatial location, and the illuminance of the object affect perception. The density of the receptors and ganglion cells in the retina is higher at the foveal area, and therefore central vision is more sensitive to observing details than the peripheral vision. Varying levels of human attention impacts human visual perception. A higher attention span has the effect of increasing SSVEP strength when a flickering stimulus is presented in the attended region of the visual field. Ionography is a technique to visualize the biological valence flux of the human visual field by using the eye itself as a camera. The participant is fitted with a wearable EEG device that has an electrode attached at the OZ location of the 1020 EEG system. The technique requires the user to fit their eyes on a particular location while a stimulus traverses across the participant's visual field in a grid-like fashion. SSVEP responses are obtained at every grid point location. These response activation values are mapped onto their corresponding spatial locations. This process repeats at varying distances from the user to construct a map of human visual perception. This study has 2 different types of ionography. These are shown on this particular figure. A hardware-based one, which is on the left side, and a software-based one, which is on the right. We are using these 2 approaches to prove the concept and investigate the human visual field. The typical implementation of hardware-based ionography utilizes the sequential wave imprinting machine technique, also known as the SWIM technique, to overlay the visual field onto the desired spatial plane. Typically, SWIM uses an array of light sources that move back and forth to visualize invisible physical measurements and phenomenon. The apparatus operates using 2 stepper motors and a belt assembly to move an arm in 2 dimensions within the bounds of its operation. The arm connects to a display device with a flashing stimulus at a set frequency. The plotter receives position vectors at regular intervals as the stimulus flashes. The stimulus moves in a zigzag pattern from bottom to top, then back, and repeats. Or a unidirectional pattern starting from bottom to top, and then resets to the next bottom position. The user focuses on the approximate center of the apparatus as the stimulus traverses through the different predefined positions. Once the system collects the EEG data for all the predefined points, it constructs a mapping of the visual field of the mind's eye. The apparatus is then fitted with an RGB LED to trace out the mapping of the visual field. As the LED traverses, different colors are produced depending on the strength of the SSVEP response at a given position. The obtained result is a two-dimensional augmented reality ionograph by capturing the entire LED tracing process with a long exposure photograph. The software ionography makes use of a computer monitor as a two-dimensional plane. The user focuses on fixed graticule in the center of a black background, while the screen stimulus of constant size flashes across the screen, traveling in a right to left and top to bottom manner. At each position, the stimulus flashes at a particular frequency for a fixed duration. Once the EEG data is collected, the subsequent SSVEP activation mapping of the mind's eye results in a 23 by 23 pixel slice of our visual field. The sequence may be repeated at various distances to the eye to recreate a three-dimensional ionograph. The lock-in amplifier is an analog device that isolates and amplifies a certain frequency while rejecting all other frequencies. This method of signal extraction is useful in an extremely noisy environment. Given the frequency that the stimulus is flashing at, two reference signals, a sine wave and a cosine wave, are multiplied to the original signal. The algorithm replicates the performance of a hardware-based lock-in amplifier. The algorithm multiplies the raw EEG data collected from the OZ position, defined as the signal UT in the equations, with the cosine and sine reference waves at the stimulus frequency to extract the SSVEP at that frequency. Then, a second-order Butterworth low-pass filter at 0.7 Hz is applied to yield an output that mostly contains the amplitude information of the signal. The low-pass filter is set at 0.7 Hz since this is approximately a decade less than the frequencies of interest. The summed magnitudes are then averaged to indicate the extracted value of a particular spatial location. A simple threshold denoising algorithm is applied after applying the LIA algorithm to isolate quantifiable features on the resulting bitmap. The algorithm weakens values below the threshold and strengthens the values above it. Next, by comparing each pixel value to its neighboring pixels and removing outliers, the single pixel noise is removed. Lastly, the method averages the pixel value among the neighboring pixels and by applying a Gaussian filter to the image. The images shown here are examples of the thresholding results. There are 5 participants in the experiments, 4 males and 1 female in their mid-20s to early 30s. All participants are not diagnosed with any brain or vision-related issues. Users C and D wore prescription corrective lenses during the experiments. Table 1 lists the software ionography experiment variations for each user. During the experiments, the users focus their vision on a centered indicator, while the stimulus moves to different predefined locations. At each predefined location, the stimulus flashes for a set duration of 1 second or 2 seconds for the software ionography and 2 seconds for the hardware ionography experiment. In the software ionography experiment, a 200 by 200 pixel black and white flashing circle moves left to right for each predefined row, and then top to bottom. The stimulus size is dependent on the user screen size as shown in the table. The experiment is repeated at 20, 30, 40, and 50 centimeters away from the screen to reconstruct a three-dimensional field of vision. In the hardware ionography experiment, a square stimulus is displayed using a cell phone fixed on the apparatus with a screen size of 12 centimeters. The hardware ionography apparatus plots the results with an RGB LED so that the resulting LED trace can be visualized using long exposure photography. The signals are processed using the software-defined lock-in amplifier algorithm to extract the SSVEP and obtain the pixel value for each stimulus location. Then, the VisMap is plotted onto a heat map based on values for all locations. The example software ionography shown on the top right is taken at 18 Hz stimulus frequency and 2-second duration by user C. Each of the VisMap portrayed the existence of a foveal area. This foveal area had a higher SSVEP activation, forming a circular pattern within the participant's field of view, and corresponded to the higher intensity color. The bar graphs show the retrieved foveal areas for each user's VisMap. For results in which a clear foveal area is not visible, the results are recorded as 0 pixels. Data taken at 1 second stimulus duration had a higher rate of noise in the foveal area compared to data taken at 2-second stimulus duration, since the higher stimulus duration had more sample points per stimulus location. The lock-in amplifier algorithm had more data to work with for signal extraction and noise filtering. These are the set of hardware ionograph images that we have produced for collected EEG data. The ionograph images are augmented reality overlays of the visual field of the user. Figures A and C are collected using the zigzag pattern described earlier, while B and D are collected using the unidirectional pattern. The stimulus frequency for user B is set as 17 Hz, while user C is set at 18 Hz. The stimulus duration for all experiments is set at 2 seconds. In both hardware and software ionography, the SSVEP response peaked when the stimulus was flashing close to the central vision, the focal point. The foveal area was found to depend on the stimulus distance, size, and duration. In the software ionography, the focal point is represented by a circle of high activation in the center of the VisMap as shown on the top figure, while in the hardware ionography, the focal point is represented by lines of high activation near the center of the SWIM, as shown on the bottom figure. Using the hardware ionography, it is also possible to produce a rough eye tracking sketch. That is, we are able to visualize the direction of the participant's gaze and focus. Here, you see in the left a figure of a participant looking at a downward angle during the experiment. On the right, the same participant is looking straight across. The resulting ionograph reflects these changes in the direction of the participant's gaze. There are 2 interference sources observed in the experiments. The subjects reported difficulty in following the procedure for the hardware ionography experiment. The difficulty was due to the absence of a display that is coplanar to the stimulus. Subjects are required to refocus their vision whenever the stimulus enters and leaves their central field. Unfocusing and refocusing many times may cause changes in their attention levels and reconfigure their line of sight. These changes may decrease the SSVEP response strength. A human blink occurs at frequencies of 6 Hz and lower and strongly affects human visual perception and EEG signals. Blinking affects visual perception since the individual momentarily loses sight of the stimulus while the eyes are closed. The muscle signals sent to the eye during a blink will interfere with SSVEP. The EEG amplifier will pick up this muscle signal as noise. This could have resulted in noisy data obtained at the 6 Hz by user A. A delay between the time of presentation of visual stimulus and the activation of SSVEP was observed in the results of the hardware ionograph. This delay is called the response delay of SSVEP. The delay is clearly shown below through the results of 2 different moving patterns of hardware ionography. When the stimulus moves in a zigzag pattern, SSVEP response shifts up and down according to the direction of stimulus movement. In contrast, when the stimulus moved in a unidirectional pattern, the start position of the activations were more aligned. These contrasting observations imply that the SSVEP activations were shifted equally in the same direction in the unidirectional pattern ionographs. As a result of unidirectional shift, the area of activation in unidirectional pattern ionographs must have inherent inaccuracies that are difficult to account for in isolation. However, with the addition of the zigzag pattern ionographs, it is possible to estimate the true center of activation. By assuming response delays is equal in both directions, we may average the results of rows moving in different directions. The distance from this average to the shifted activations is the response delay, while the average center is the direction of the participant's gaze. This paper provides an exploration of SSVEP frequencies, human vision, and response times. Wearable EEG devices can do more than just track users' sleep patterns, mental states, and cognitive health. Through the use of ionography, EEG devices can also examine the foveal area of the human eye. This opens a potential path to personalized eye health informatics, perceiving and quantifying the visual acuity of the human eye. Ionography is a technique to visualize the visual field of the human eye as it changes in space. 2 types of ionography are presented, a software-based and hardware-based. The software-based ionography is constructed with multiple viz maps at various distances. Each viz map represents the SSVEP responses obtained by displaying a moving, flickering stimulus at a particular distance from the eye. The hardware ionograph is a 2-dimensional augmented reality overlay that is produced using long exposure photography and an LED tracing procedure to represent the SSVEP responses from a moving, flickering stimulus. Based on the results presented, the ionography method sufficiently captures the participant's focal point and attention. The foveal area remains largely static over distances, while a longer stimulus duration returns a less noisy signal for data collection. The existence of a response delay for SSVEP can be shown via the hardware ionograph. The unidirectional pattern ionograph shows a straight beam of activation from left to right, while the zigzag pattern ionograph shows shifted activations based on the stimulus direction. Due to the pandemic at the time of submission, it was not possible to coordinate many aspects of the experiment unilaterally. Factors such as screen size, resolution, postures of participants, and other hardware or personal differences could have potential influence on the end result. In the future, these factors may be controlled or eliminated as desired to advance our understanding of human perception. SWIMS, sequential wave imprinting machines, in general have been used for visualizing phenomenological realities that are otherwise invisible to the human eye, by showing its usefulness in visualizing the human visual field. A future direction may include plans for using this augmented reality method to explore and visualize other biological phenomena. This future direction may include an example would be auditory perception of the human ear. Ionography can help determine the visual acuity of a person and quantify how eye defects hamper vision. As it directly measures perception itself, this method of visual perception analysis can lead to new insights into correlations between vision and cognition. Future direction can potentially lead to cognitive visual exercises, brain-computer interfaces, or perhaps even explore visual perception within dreams. Ionography can develop for use as an eye health assessment tool. When one visits the eye doctor, some degree of subjectivity in the form of user testimony is still present. Assessment by ionography is more objective and accurate. By using a wearable EEG device, the assessment method becomes more accessible and cost-effective, both in terms of assessment time and economic cost, over traditional non-wearable neuroimaging devices. A particular interesting area of study is again the potential for discovering color blindness by flashing different colored stimulus at the patient. Thank you for taking time to listen to our presentation. Special thanks to Jesse Hernandez for his valuable advice, opinions, and also assistance to the project. Authors also would like to thank other members of ManLab Canada for their continued support. Thank you.
Good morning everyone, my name is Luca Gioacchini and I'm a Master Science student in the ICT for Smart Society course at Politecnico di Torino, and today I'm going to present about sensor characterization for a calibration-free connected smart insole for healthy aging. First of all, I'll introduce the social context of the work, the related works and the motivation. Then I'll show you the sensors we have characterized, highlighting the adopted methodologies. Then we'll discuss the obtained result and the conclusions. Our work arises from the demographic transition occurring from more than 10 years. It consists on the strong presence of elders, which now is 10% higher than the number of young people. Because of this demographic aging, the resources required for the elders' assistance are drying out, and the need of monitoring devices able to improve their life is emerging. According to the targets, the appliances should be easy to use and possibly without the need of uncomfortable calibration step. So, to fulfill this need, researchers have been focusing on applications concerning clinical scenarios, but all the considered technologies require complex calibration processes and expensive instruments. Moreover, the studies pay more attention on the device's electronics or on the way of transmitting data and making the equipment connected instead of approaching the sensor's characterization. Only a few smart insole devices are sold in the market, and they are mainly addressed to sport applications such as running or jogging, in order to help people improving their performance and also their health through sport activities. To such an aim, the devices need to measure the user's step length and other figures related to gait and body shape, and for these reasons usually a calibration procedure is necessary. The user has to run on a treadmill according to predefined patterns on velocity, and such modality could be not always feasible in case of older adults. That's why we aim for a calibration-free device, which of course will prevent us from measuring some figures such as the distance traveled. In this work we focused on the development of smart insoles. These wearable devices can be inserted into a user's shoe, and they enable in a minimally invasive fashion both the detection of physical activity by the older adult and its classification, as well as the step counting. So, according to the aforementioned requirements, we adopted a calibration-free approach, making the Insole a sort of plug-and-play device. To accomplish this and to fulfill the research gap, we propose a metrological characterization of two pressure sensors to get the design choice. The considered sensors have been tested during the Insole development from the first prototype up to the final wearable device, which can be tested by users. So, the first sensor is the FlexiForce A301 by TechScan, made of a piezoresistive material between two conductive layers. When the user applies a pressure, it changes the resistor length, making the resistance values changing accordingly. From the datasheet, the maximum loads changes according to the used model, from 4.4 Newton up to 445 Newton. The long-term drift is less than 5% per log base 10 of time. The second sensor is the FSR 402 short, suitable for do-it-yourself projects, for example with Arduino boards. It is based on the thick film technologies, thus two conductive layers are separated by a spacer. So, by applying a voltage to the layers, when the user applies a pressure on the bottom one, the conductive elements short together, generating a variable resistance. Then from the datasheet, 0.2 newtons are required as activation load, and the maximum tolerated weight is 20 newton. Even in this case, the long-term drift is less than 5% per log base 10 of time. To perform the sensor's characterization, the resistance values are collected by applying a 5V power supply from an Arduino Uno board and by performing an analog read through the voltage divider of the same board. To obtain the amount of the applied newtons with high accuracy, a dynamometric platform is used as reference. Its sampling rate is 500 Hz, and this value is higher than the 20 Hz of the Arduino boards, so a downsampling is required. Then, the measurements were performed by focusing the weight on the sensors through a supermedium, and in correspondence of a vocal trigger of an operator, the acquisition started. At this point, we performed three kinds of characterization. The illustrated setup was used for heavy weights characterization, applying an increasing amount of 10 and 1 kilos weight plates. For the low weight, a light wooden support was used to focus the weights on the sensors. The reference instrument was a kitchen scale, and an increasing amount of 0.1 kilos of water-filled elements was applied. Finally, the drift factor is evaluated by applying 3 kilos on the FSR and 23 kilos on the A301 for 60 seconds. The different weights are used to ensure the linear working zone of the sensors. Regarding the weights characterization, we investigated the mean values of the resistance assumed by the sensors during each measurement operation. First of all, only the 3 kilos medium is applied, checking that the offload measurement ensured the linear working zone for both the sensors. From the plots, it is clear that the FSR assumes a resistance value of 0.68 kΩ, which is much lower than the FlexiForce one of 225 kΩ. When 13 kilos are applied on the FSR 402 short, it enters the saturation zone. The standard deviation reported as the measurement error bars shows that in this condition the values floating are very small, and this behavior persists even by adding increased amount of weight. Indeed, the measured values decrease a little down to 0.16 kΩ floor. On the other hand, the A301 sensor is still in its linear working zone according to the datasheet. The resistance force curve exhibits a slight concavity and a little offset corresponding to the 13 and 15 kilos, meaning that the range of assumed values is still wide. For example, by applying 146 Newton load, a resistance value of 76 or 79 kΩ is obtained, whereas for a 327 Newton load, the resistance value is approximately 53 kΩ. Thus, from the first measurement, it is clear that the FSR 402 is less sensitive to high weights, while A301 is still in linear working zone by applying even 33 kilos. Different results are obtained when low weights are applied. The FSR 402 is more sensitive to low weights variation. Indeed, apart from a little offset when 2.1 and 2.2 kilos are applied, the empiric trend shown in the plot is coherent with the one provided by the datasheet. On the other hand, when characterizing the A301 sensor, it does not work until 0.5 kilos are applied. Moreover, by increasing the load, the standard deviation is greater than all the other cases, and the recognizable trend is not reported by the plot. So this irregular behavior can be explained by assuming that the activation load was not reached, and so the output is not reliable. When evaluating the drift factor with a 60-second long static measurement, the sensors are firstly kept in their linear working zone. The drift is determined by comparing the first and the last resistance value of each measurement. So, by considering the A301 values, they float over different values. And after 60 seconds, the average drift factor is about 5.22% of the initial value, which is slightly greater than the maximum 5% reported by the datasheet. On the other hand, by evaluating the FSR 402, the average drift factor is 3.33% of the initial value, which is lower than the datasheet one. However, in this case it is necessary to consider that even if the FSR is in linear working zone, it is approaching the saturation, thus the floor values is limiting the range of possible values. Finally, when considering both the linear and the saturation working zones of both the sensors, it is clear that the FSR exhibits a lower drift factors, allowing only 6 discrete values in linear zone and 3 values in saturation. On the other hand, the A301 range is wider with 12 possible values in linear zone and 8 values in saturation zone. So, from the experimental result, it is possible to target 2 kinds of application by the examined sensors. In case of application exploiting the sensors as switches with respect to a certain thresholds, both the FSR and the FlexiForce A301 are valid. On the other hand, in case of application requiring a measure or an indication of the applied weights, the FSR is more suitable for low weights application, such as the ones requiring touch-based interactions. Regarding the A301, it is more suitable for high weights application with low sensitivity. So, in light of the above, we decided to equip the Smart Insole with the FSR 402 short, aimed at detecting different activity statuses. Raw data are not transmitted, but they are processed by the board in the Smart Insole. When a change in the activity status is detected, a signal is then transmitted. Regarding the future development of the device, it involves the integration of an accelerometer to improve physical activity detection and the evaluation of the daily walk distance. So, that's all. Thank you for your attention.
Hello everybody and welcome. I am Tiziano Foppanni and I'm here to present our paper, Novel Wearable System Fast Phase EMG, using compact electronic board and printed matrix of electrodes. So let's start with a brief introduction. The human body produces plenty of signals that can be used to and employed to understand the physical status of an individual. Obviously, there are plenty of those signals, some of which are depicted in this slide. Among those signals, we discriminate electrical, EMG or ACZ for example, and non-electrical ones, like the body temperature. Obviously, all those signals can help us to understand our health status, and they can provide information to a clinician on how to diagnose a disease to a patient. To us, one of the most interesting signals is EMG, or electromyography. The signal is related to the muscular activity and can be used in a plethora of applications, both in clinical practice and outside it. For example, it can be used to diagnose muscle misbehavior, track the progresses of a rehabilitation patients, or even trigger active devices such as human-machine interfaces or prosthetics. EMG signals can be sampled in a really simple way, and those techniques are widely known in the medical practice. However, those standard techniques are usually uncomfortable to the user and require bulk instrumentation. Thus, they are unsuitable for long-term monitoring or even on-the-field measurements. A different approach is using wearable devices. According to this paradigm, we want to embed an electronic device inside the clothes of patients, or in a device that they can comfortably wear. Those devices are thus very comfortable to the user and they enable a lot of applications like long-term monitoring even outside a medical environment. Some possible applications of EMG wearable devices are reported in the slide. For example, in the rehabilitation field, the signals from the muscle can be displayed, even as serious games, to help the patients understand how to correctly perform the exercises. In this context, they also can provide a feedback to the clinician to track the effectiveness of the treatment. Another application that's reported in literature is the evaluation of neck fatigue, or more in general, the detection of incorrect postures. These applications are relevant to improve workspaces and, in general, workers' life. Moving then towards the human-machine interfaces field, different applications are suggested in literature. Those can be applied in medicine, like in prosthetic control, but can also embrace different topics, like silent speech recognition, or the discrimination of wrist gestures that can be applied in robot control or virtual reality applications. The wearable devices are a game changer then in all these applications, but their development opens different challenges. To improve the usability of the device, the power management systems must be chosen to provide enough battery life without interfering with the user comfort. In order to follow this second paradigm, it is important to reduce the device encumbrance and fit the electronics, battery pack and sensor in a small form factor and in a lightweight device. Last but not least, the sensors that interface the human body must be biocompatible and provide good sensibility and stability under a variety of conditions like temperature, humidity, movements on the body, etc. Our work is done to build a device that follows two paradigms. At first, we want to improve the quality of the collected data, and then we want to optimize the user comfort. To do this, we develop a wearable device for EMG that will be compliant with the specifics presented in the slide, as improve the collected data and optimize the user comfort. In particular, we want to develop an 8-channel device with a wireless data transmission that presents a small form factor and a flexible electrodes. The flexible electrodes are fundamental to us to improve the conformability of the device to the human body and thus increase the device performances. Moreover, flexible electrodes produce lighter devices because we use substrates that are less heavy than usual. Moreover, those printed electronics techniques permit to limit the product wastage Among the possible printing techniques shown in the figure, we must distinguish between contact and non-contact printing. Each technique has its pros and cons that varies between the different inks, the process speeds, or the feature definition. We decided to employ aerosol jet printing, a non-contact technique that empowers some interesting possibilities. This technology allows the printing of features with a wide set of characteristics, ranging from 10 micrometers of width and different thickness. Moreover, it is able to work with inks with a wide set of viscosities. These techniques employ a gas to optimize the functional ink that is conducted to an impactator. The ink particles are then deposited through an annual gas flow that prevents the clogging of the nozzle. Without wasting more time, let's talk about the device architecture. Here in this slide, a standard architecture for a wearable device is shown. It presents two units, a wearable one and an external. The former is one on the subject and senses all the signals. It also embeds a microcontroller to perform different control operations, some sort of power management and communication device that send all the data to the external unit. The other unit has to retrieve all the information to another communication layer, and then it has to store, display, and elaborate the data. So let's start an in-depth analysis of the implementation of the two units, starting from the wearable one. The scheme that we follow to implement the wearable unit is depicted in the slide. Attached to the user, there are some sensors that provide signals to an analog front end. This front end conditions the input analog signals and prepares them to be fed to the analog digital converter. After the digitalization, the data are sent to a microcontroller, who stores and transfers them to the remote unit. Moreover, a power management unit helps extending the device battery life. The sensors were produced using the above-mentioned aerosol jet printing technique. To produce low-resistance tracks and pads, a silver nanoflake-based ink by Novacentrix was selected. Moreover, to produce a conformable and biocompatible patch, photographic paper was selected as substrate. Moving towards the production process, we performed some preliminary tests in order to tune the several deposition parameters, some of which are depicted in the table. This optimization process allowed us to achieve regular printed tracks with well-defined widths and thicknesses. To make the electrodes conductive, the printing process was followed by a temperature curing step that was performed in a preheated oven, as suggested by the manufacturer. The electrodes design was drawn using AutoCAD. We decided to arrange the electrodes in a 4x4 matrix configuration. This arrangement allows us the measurement of signals from different parts of the body, and thus to provide more information on activation patterns of the muscles and on the signal propagation on them. Each pair has a 3 mm radius, and each row presents a 12 mm spacing between each other. The whole electrode matrix is around 5 by 5 cm wide, and that includes the tracks needed for electrode connection to the electronic board. Among the possibilities to implement the communication layer, we decided to employ Bluetooth Low Energy to obtain both low power consumption and enough data rate to perform a real-time data transmission. We implemented the communication using a compact 1 by 1 cm Cypress microcontroller that embeds a Bluetooth Low Energy chip that is the stack development. We also use the microcontroller to retrieve the information from the analog to digital converter and control the whole wearable unit. To reduce the number of components, we employed an integrated analog front end and analog to digital converter by Texas Instruments. This chip is controlled by the microcontroller using SPI. This device provides for each channel a programmable gain amplifier with 7 possible gains and even a 24-bit delta sigma analog to digital converter with several possible sampling rates. After some preliminary evaluation, we decided to define a gain of 12 and sampling frequency of 1 kHz. Those devices, with the required additional components, were embedded in a custom PCB with a small form factor of 5 cm squared. This first prototype will be later engineered to further reduce its encumbrance. After this analysis of the wearable units, let's focus on the external one. The 4 main tasks that should be performed by a remote unit are communication, elaboration, storage, and display of the data. Our implementation is based on a USB dongle by Cypress Semiconductors that provides a basic interface between a laptop and the Bluetooth Low Energy protocol. Moreover, we choose to develop just the communication and data storage layers in real time, while the remaining tasks were later performed using MATLAB. Let's move on now to the test phase, and in particular to the transmission test. Here, we want to understand how the system performs when it must transfer the collected data from the wearable to the remote unit. To best understand those tests, it's important to know how the communication is implemented. We call a sample a 27-byte array composed by a 3-byte status word and 24 bytes for each channel, where the values of the input signals at a particular time are stored. 18 samples are then put together in a packet that also contains an identifier. This identifier is used to find missing packets on the remote unit side and thus quantify the communication reliability. Moreover, the remote unit is programmed to save a timestamp each time a packet is received. Using both this information and the above-mentioned identifier, is then possible to calculate both the average transmission time and the maximum transmission time, as well as the throughput. The results that we got from this transmission test are reported in the table. Here, we report both some of the results obtained with a sampling frequency of 1 kHz and a single test performed with a sample frequency of 2 kHz. Starting from this last measure, we can observe both a good throughput and, sadly, a high number of lost packets. This could make the communication unreliable, and that's why we choose to stick to the 1 kHz sampling frequency. Looking at those measurements, we can observe a couple of interesting things. At first, a very stable throughput with a small standard deviation. More interesting is the ratio of the correctly received packets on the total of the packets received. That is for all the measures above 99%, indicating that the system is quite reliable. We investigated even the timing characteristics. Here, we report 4 different sessions the measured mean and maximum transmission time of the packet. We can observe that the former is always around 18 milliseconds. This is exactly the time required to fill a packet with a 1 kHz sampling rate. As regards the maximum transmission time, however, we can observe values well above 15 milliseconds, and that's why an output circular buffer was inserted to prevent the loss of packets. Extracting then the average on all the measurement sessions, we can observe an average of 63.4 millisecond maximum transmission time, with a standard deviation of 7 milliseconds. As regards the average transmission time, a significantly lower standard deviation of 0.01 millisecond was recorded. Last but not least, let's talk about the proper EMG evaluation. For this step, we selected a healthy male volunteer of 24 years old. The proposed exercise required to perform maxillary contraction without changing the muscle length. Those are also known as maximal isometric contractions. We ask that the whole exercise follow the pattern shown in the slide. Nominally, it would start with a 10 seconds of rest, followed by a 30 seconds of contraction. After another resting phase of 30 seconds, we asked another contraction period of around 15 seconds. Before closing the measurement session, we again recorded a resting period. Using this protocol, we wanted to easily identify the contraction event. To validate our architecture, in order to do this, different digital filters and elaboration steps were later performed on the recorded data using MATLAB. Without wasting more time, let's give a look on the collected signals. Here, we selected 2 channels on the 8 available. Even though it's quite easy to guess the presence of our signals, they are still measured by noise. Those are mostly due to the 15 Hz harmonics interference due to the power line that are clearly visible here before performing a spectral analysis on the signal. The spectral analysis is shown on the bottom right part of the slide. We were able to get rid of them using a set of digital notch filters, whose both diagram is shown in the small figure on the right. After this filtering spot, we were able to obtain the red tracks reported in the big image. Looking at them, we can observe that we get rid of most of the noise on the resting periods, and of weighted baseline effects like in channel 8. Obviously, those filters introduce a bandwidth limitation, cutting also the DC components of the signals. This, however, doesn't introduce any problem, because the useful information for surface EMG is usually above 10 Hz. In the end, the retrieved signal is the one shown in the figure. Here we can observe some spikes, probably due to the movement of the recording cables. Moreover, here are clearly visible the contraction and the resting periods that can be easily mapped to the exercise plan we described above. In fact, here we are able to clearly identify the 3 relaxing phases and the 2 contracting ones that are already visible without any kind of further elaboration. At last, we analyzed the spectral components of our signals, performing a fast Fourier transform. According to this analysis, we were able to verify that most of the power of the EMG signal is stored before 150 Hz, like we already noticed in the literature. Moreover, we decided to analyze the resting and the contracting phases separately. As depicted in the figure, the resting phase, in red, has significantly lower values in all the spectrum than the contracting phase that is depicted in blue. We then used the 2 sections to calculate the signal-to-noise ratio that results around 28 decibels. Summing up this presentation, we were able to demonstrate the production of a multi-channel front-end for EMG acquisition based on a flexible matrix of electrodes produced by aerosol jet printing. Our device is able to sample 8 channels at 1 kHz and provide the collected data real-time through a wireless communication channel, achieving an optimal transmission reliability. Further steps will include the engineering of the device to further address its encumbrance and improve its conformability to the human body. Moreover, different applications are at the moment under investigation for rehabilitation and other clinical applications. I just concluded my presentation. Thank you very much. I am available for any kind of question.
Hello everybody. My name is Aisha Rizzuti Kadouri from the University of Applied Science in Switzerland. Today I will present our article titled Stress Detection with Deep Learning Approaches Using Physiological Signals. This work is part of one research project in our university. The ultimate goal of our project is to develop a system able to quantitatively evaluate stress levels in non-invasive and continuous manner by means of wearable devices. The system should inform a user about their stress level in an adequate manner, such that it does not induce additional stress to him or her. Stress is usually defined as a feeling of tension and pressure, and continuous exposure to stress is detrimental to mental and physical health. However, at a physical level, stress is a natural reaction of the organism to external stimuli, helping to defend in dangerous situations or achieve certain new goals. Once the dangerous situation is over or the goal is achieved, our body returns to a normal state homeostasis. Nevertheless, there exist many studies showing the link between stress and illness. Detecting and managing the stress level has a clear positive economic and societal effect for an organization by improving the work performance and reducing the number of complaints. In this kind of project, data is important and the quality of data is also important. After determining which physiological signals are going to work with in our project, those main signals: heart rate variability, HRV, and transpiration observed by the galvanic responses of the skin, named electrodermal activity. HRV provides a good measure of parasympathetic nervous system, PSNS, activity, and EDA, or galvanic responses measures, can be assumed to reflect sympathetic nervous system, SNS, activity. The signals were acquired from 6 students of our university who have signed the consent form, and the study protocol was approved by the Ethics Committee of Human Resources in Switzerland. Several features are extracted from the 2 signals and several stress prediction algorithms are evaluated. We used the resource bracelet of the Empatica. Here you have the imported sensor for our project, like PPG sensor, photoplethysmography sensor, measures the blood volume pulse, BVP, from which 2 important signals can be derived: heart rate, HR, and the interbeat interval, ABA. The blood volume pulse is measured in nanowatt, the heart rate, HR, in beats per minute, while ABA is measured in time period between 2 consecutive beats. The second signal sensor, EDA, or galvanic skin response sensor. The skin is the only tissue of human body that is innervated by only SNS branches of the ANS and not by PNS branch fiber. Activation of the SNS provokes activation of sweat gland and thereby reducing skin electrical resistance and increasing conductance. Whose fluctuating changes are measured by the EDA sensor in Siemens. Consists of two signals, tonic component and phasic component. For tonic component, referred to as skin conductance level SCL, and a phasic component skin conductance response SCR. In order to perform experiments, we have developed our proprietary mobile application for Android mobile platform with a user-friendly front end and a backend performing three basic features such as data collection from the Empatica A4 bracelet and its temporal storage at this smartphone. Questionnaire allowing to collect the perceived level of stress by each participant and a secure transmission of the record data into a web application, medical application, REDCap database. Here you see our architecture for the data flow in our data processing chain is presented like that. It starts with the raw physiological signals collected from these bracelet sensors, which are further sent to the mobile application. Next, the data flow is securely sent to REDCap platform. REDCap platform is a secure web application for building and managing online surveys and databases, frequently used and recommended for managing medical data. The data are stored in the cloud for further extraction of various features using proprietary signal processing. The feature as extracted and are sent to the REDCap cloud. Further, the data are picked by a classification algorithm capable of predicting the stressful event. The study protocol was approved by the Ethics Committee on Human Resources in Switzerland, and data set consists of 6 patients, each with a duration of about 44 minutes. To avoid artifact, the experiment was performed in laboratory in this phase. There are different types of stress. We selected stress from emotional arousal, intellectual effort, physical exercise, and pain. Emotional arousal was stimulated by showing a scarce video during about 3 minutes. Intellectual effort was done by solving some riddles that were chosen by each participant randomly from a bunch of riddles printed on paper, 2 to 3 minutes. Physical activity was represented by a series of squats, and pain was emulated by letting the participant to put his hand in the icy water for 1 to 3 minutes. After each period of the experiment, whether it is a relaxing period or a stressful period, each participant was asked to report their perceived stress level regarding the just finished activity, describing it as 1. I feel more relaxed, no difference. 3. I feel less relaxed, and I feel more stressed. This annotation will be used to annotate our machine learning model. As you can say in here, a sequence of stressful and relaxing events with questionnaire. For the features used in this project, the main signal used for our prediction for machine learning were ABA and EDA. We have extracted the most important features related to stress. ABA signals is often also called HRV. If you look at the ABA signal of the Empatica, you will find data that is sometimes missing. We have implemented the algorithm which reconstructs the missing data, and we extract several features in different domain, time domain, frequency domain, and geometrical method, for example, standard deviation, etc. The second signal is EDA, electrodermal activity. Regarding the EDA signal, and as I said before, we worked on the two tonic and phasic components. The phasic is more relevant in our cases, and suddenly we extracted the feature which the phasic component. Those features extracted in time and frequency domain. As you can say in here, for example, ADA peak count, if the number of local peaks increase, the stress increases. For process learning, we decide to compare three different methods: a decision tree model, a recurrent neural network RNN, and a third, an augmented RNN with some convolutional layers. Our classification of stress is achieved with a recurrent neural network and yields a macro F1 of 71%, as you can see here. We have a lot to do to improve our research in this project. We need to collect more data to better test our algorithms, and if possible in the field we will have better indication of stress for each person. Measuring cortisol can calibrate our model, since it is a measure that gives a good indication of stress even if it is invasive. Our dataset will include the contextual data as well as measurement of cortisol. Study on and assessing stress is an important topic today, and preventing stress can help many people. Thank you for your attention, and if you have questions.
Hi everyone, my name is Angelica Poli. I am a biomedical engineer and I am currently enrolled as a PhD student at the University Polytechnic of Marche in Ancona, namely at the Department of Information Engineering. My research interests are related to the electronic instrumentation and measurements, and today I'm going to talk about the preliminary results of an IoT-enabled EDA-based analysis of physiological response to acoustic stimuli. In details, I'm going through a brief introduction, then I'm explaining materials and methods used to perform our experimental tests, then I'm explaining the results and discussion, and finally the related conclusion. Since many decades, human emotion recognition has gained growing worldwide interest in many application fields, especially for developing consistent techniques to do this aim. A reliable approach designed using the physiological signals can help to derive and detect the objective measurements and also to detect the actual emotional changes of subjects. Today, the galvanic skin response signal, named also electrodermal activity, along with the development of IoT-enabled wearable devices with wireless technology, able to measure physical and physiological processes, allow to detect and monitor easily the subject's emotions and consequently the reaction to different types of stimuli. However, many studies are mostly focused on the emotion classification and recognition, performed by extracting features to feed and test several machine learning algorithms. According to literature, in order to obtain a high performance from such automatic approaches to emotion detection, a detailed analysis of the galvanic skin response measurement data for the properties is essential. Therefore, we propose a preliminary study to investigate the morphological characteristics of the GSR physiological curve, focusing on the responses elicited by acoustic stimuli of different valence. GSR signal can be exploited to measure the sympathetic activity and consequently to have a feedback on those hidden mechanisms that occur out of our control. But how does it really work? EDA is the measurement signal of the continuous changes and fluctuations in the electrical activity of the skin properties in response to external arousing stimuli. This figure shows a sample of GSR or EDA signal in time domain, characterized by two components, the tonic one, which varies slowly, and the phasic fast response, which can be event-related. Today, as I said before, the variations of the electrical properties of the skin can be measured in an easy and non-invasive way, applying a low constant voltage on the skin surface, especially with the help of two electrodes. Indeed, Empatica E4, that is the wrist-worn device clinically validated that we used, is able to capture electrical conductance across the skin by passing a minimal alternating current between two electrodes that are in contact with the skin. E4 operates in streaming mode to visualize data in real time by means of a mobile app called E4 Real Time, running on a smartphone connected to E4 via Bluetooth Low Energy. Once a measurement session terminates, The collected data are available on the cloud platform E4 Connect. More details relative to the EDA sensor used are listed in the left side of slides. In order to measure the impact of auditory emotional stimuli, small dataset was collected from 7 individuals, both at rest condition and during the sound listening. In particular, EDA measurement data were acquired from 2 males and 5 females. For each individual, the emotional changes under 3 different auditory stimuli, namely pleasant, neutral, and unpleasant, were acquired. Audio clips were selected from the IoT database. However, while this database includes short audio clips, long segments of musical pieces have been used to elicit emotional reaction. All the sessions were recorded by wearing the Empatica E4 on the dominant wrist, while the subject was lying on a bed with closed eyes. Subjects were asked to perform 6 recording sessions, and in particular 3 sessions lasted 11 minutes and the remaining 3 sessions 12 minutes. The first group of sessions, as soon as the rest condition that we consider as a baseline was over, the sound was played through a Bluetooth speaker for 1 minute. After this, measurement data at rest conditions were again collected for other 5 minutes. Regarding the second group of 3 recording sessions, the procedure was the same, but in this case the sound was played for 2 minutes. So the overall duration of these recordings was 12 minutes. According to the literature, the steps of data preprocessing include, first of all, raw data were acquired and first and last 4 seconds were discarded, especially to remove the artifacts for the transient noise due to some potential movements of the subjects. Secondly, scanning each signal sample by sample, a sliding window median filter was computed to extract and separate the tonic and phasic components from each acquisition. According to literature, a peak and true detection algorithm has been developed to select and identify 2 thresholds of the phasic curve. One threshold to identify the onset and another to identify the offset. Therefore, an onset was identified when the phasic curve was higher than the onset, and an offset when the SCR point was lower than the offset. Then, as shown in figure, back to the original EDA signal, for each onset-offset couple, the exact position of each peak was identified and counted as peak for minutes. This represented metric was defined as peak's frequency and counted to understand how the EDA signal shape changed in both presence and absence of acoustic stimuli. Findings from the proposed algorithm are compared among the subjects. In terms of values obtained by averaging the outcomes on the 3 sessions for each participant. As shown in this figure, for each subject, the orange bar represents the peaks frequency in the first 5 minutes of acquisition at rest, so the pre-stimulus. The yellow bar indicates the rate of GSR peaks in the phase of external stimulus, and the green bar states the number of peaks per minute computed in the last minutes, so the post-stimulus phase. Although by comparing the 3 columns and the 2 rows, especially focusing on the middle phase, so the yellow bar, it is evident that the reaction determined by listening different sounds is quite subjective. We can trace some common trends. For example, regarding the pleasant sound, while the subjects S3, S4 and S5 are more sensitive to sound clips lasting 1 minute, S1, S2 and S7 are more sensitive to longer pleasant sound. By examining the effect of unpleasant sound, while the S2, S5, S7 and S7 and S6 appear to be more sensitive to unpleasant sounds of short duration, when the stimulating period was longer, that means 2 minutes, the number of peaks per minute decreases drastically, even reaching the zero for S6. However, the analysis of EDA signals measured during the listening to the neutral sound is very interesting. Indeed, 4 out of 7 participants show an average peaks frequency that increases from 0 to higher values under longer stimuli. Further confirmations of different effects on the EDA signals of the listeners are observed depending on both the valence score and the length of the audio clip. In this case, the peaks rate was averaged over all the participants in order to obtain a single value for each sound listened to. Looking at the effects of unpleasant sound stimulus lasting 1 minute, we can see an increase of EDA peaks per minute during the period of sound listening. That is the middle phase. And then it returns close to the starting values considering the lasting phase after the sound listening. On the other hand, slight changes and variations are observable in unpleasant sounds lasting 2 minutes, as well as when using neutral or pleasant sounds as external stimulus. Therefore, we can conclude that our preliminary results confirm that physiological changes in EDA signal are evident in response to acoustic stimuli. These aspects in our time domain analysis, especially evaluated in terms of peaks frequency, could be reflected in low valence and high arousal for the unpleasant sound, and instead high perception of valence and low arousal for the pleasant sound. On the other hand, neutral sound did not show general common findings, but more randomly distributed. Additionally, we also found that the same reaction when the external stimulus is too long can be affected by the habituation phenomenon, resulting therefore in a lower number of peaks per minute in the EDA curve. Although the results of this preliminary experiment are promising, more accurate findings can be achieved by enrolling a wider and more heterogeneous population, especially in terms of gender and age. For example, the different perception of an external stimulus and consequently the resulting EDA fluctuations can be compared among males and females of different ages. Additionally, also selecting more soundtracks of the same valence scores from the database can allow us to obtain more generalized and reliable findings and outcomes. Thanks for your attention. This is my email address, so if you have any questions or comments, they are very welcome. Thank you.
Hi everyone, my name is Raquel Sebastião. I would like to start by thanking the organizers for this event and to thank the audience for the opportunity of sharing this work. I am a researcher at the beautiful University of Aveiro, and today I am presenting the work entitled Classification of Anxiety based on electrodermal activity and heart rate. Let me start with a little bit of context. The recent global increase of anxiety disorders and the rise of the consumption of antidepressants demand that awareness and attention need to be devoted to mental illness. Coping strategies to deal and manage with anxiety are crucial. Indeed, in 2019, anxiety disorders were estimated to affect 4% of the world population, mostly women. These have serious implications in quality of life, daily activities, workplace, families, and society. Nowadays, anxiety disorders are affecting 300 million people, with an increasing trend and cutting across all age groups. For instance, in Portugal, it affects 9% of the population, which is a high percentage when comparing with worldwide data. According to the Organization for Economic Cooperation and Development indicators, in 2017, Portugal was the fifth country with the highest consumption of antidepressants, around 100 daily doses per 1,000 people. This clearly reveals the increase of incidence of these disorders when compared to the year 2000, when the consumption was around 1/3. This raises several concerns and motivates this work. There are several works in literature which classify or predict anxiety states through physiological signals. But most of these works use data gathered during tasks specifically designed for effect elicitation. Apart from those works, the goal of this study is to classify anxiety through physiological signals from data without any effective state elicitation. Sensing wearable devices grant the easy and on-the-fly measurement of physiological signals. Therefore, Such a classification system can be easily integrated with a mobile application to provide self-management strategies to deal in real time with anxiety symptoms. Let me describe the dataset. We had used the WEDSAID dataset, which is a public available dataset collected during a laboratorial protocol designed for stress and effect detection. This multimodal dataset contains self-reports, motion and physiological data of 15 participants recorded with 2 different devices. The Empatica wristband, which records electrodermal activity, body temperature, 3-axis acceleration, and blood volume pulse, and with the Biosignal Plux Respiband professional device, which gathers electrodermal activity, electrocardiogram, electromyogram, respiration, body temperature, and 3-axis acceleration. In this study, we used only the data collected during the baseline condition, which aimed to reflect a neutral affective state. In the protocol of the WEDSAID dataset, during the baseline state, the participants were sitting or standing at a table with neutral reading material. We relied only on the electrodermal activity and heart rate collected with the Empatica wristband, and as a ground truth for class identification, we used the response of participants after this baseline condition to the shorted 6-item state questionnaire. In this 6-item state trait anxiety inventory, the participants evaluate the following questions. I feel uneasy, I feel nervous, I am jittery, I am relaxed, I am worried, I feel pleasant, with a score from 1, which means not at all, to a score of 4, which represents very much so. This means that the questionnaire varies from a minimum score of 4 to a maximum score of 24. As I told you before, we had used only the baseline condition, which had a mean duration of approximated 19 minutes. In this histogram, we can see the distribution of the site anxiety scores, which in this dataset ranges from 10 to 16. It can be observed that the majority class corresponds to a score of 12, while scores of 15 and 16 are the minority classes. We can also observe that this data is not equally distributed. Despite of that, in this work, we didn't use any technique to deal with imbalanced datasets. Instead, we relied on other evaluation metrics rather than accuracy to assess the performance of our classifier. This figure shows the electrodermal activity and heart rate signals for participants with minimum and maximum scores of anxiety in the 6-item site questionnaire. For these 2 participants, from the heart rate signals, we can't observe any pattern or trend. However, we can see a considerable differences regarding the electrodermal activity, which is significantly higher for the grade site questionnaire score. Now I will show you the methodology and results obtained. We started by analyzing the box plots showing the distribution of electrodermal activity and heart rate values of the 15 participants according to the anxiety scores. With 90% of confidence, we can see that the electrodermal activity medians of scores 11, 12, and 16 are different, as the notches in the box plots do not overlap. We can also observe that electrodermal activity associated with anxiety scores 11, 13, and 14 present a higher variability, while electrodermal activity from anxiety scores of 15 and 16 present smaller variability. For an anxiety score of 12, electrodermal activity had a great number of outlier values. With respect to the heart rate, we can see that medians of site scores 10, 11, 12, 14, and 15 are different because the notches of the box plots do not overlap. We can also notice that scores of 10, 13, and 15 present a great number of outliers, while when anxiety scored 12 and 14, despite without outliers, the heart rate presented higher variability. To further analyze if the median values of electrodermal activity and heart rate from the different anxiety scores are significantly different, we performed the Kruskal-Wallis test. We applied this non-parametrical test after verifying that data is not normal distributed through a Lilliefors test. The Kruskal-Wallis test rejected, with a significance level of 1%, the null hypothesis that data, either electrodermal activity and heart rate, from the different anxiety scores came from the same distribution. Since the Kruskal-Wallis test allowed us to conclude that median values of electrodermal activity and heart rate from the different anxiety scores are significantly different, we performed multi-comparison tests to see which from the 7 groups of anxiety scores are significantly different from the others. For electrodermal activity, we can conclude that groups 12 and 14 have mean ranks significantly different from all the other scores. We can see also that scores 10, 11, and 15 only presented mean ranks significantly different from scores 12, 13, 14, and 16, and that scores 13 and 16 have mean ranks not significantly different from each other, but different from the remaining 5 groups. With respect to the heart rate, we can see that scores 11, 12, and 14 have mean ranks significantly different from all the other scores. Scores 13 and 16 present mean ranks not significantly different from each other, but different from the remaining 5 groups. And that anxiety scores of 10 and 15 present mean ranks not significantly different from each other, but different from the other 5 groups. So we can conclude that using both signals to predict anxiety score would be an advantage, as one surpasses the drawbacks of the others. After verifying that median values of electrodermal activity and heart rate from the 7 anxiety scores are significantly different, we moved forward to the classification task. At first, to decide on the best method for classifying anxiety scores, we constructed a predictive classification ensemble using all the available predictor variables of electrodermal activity and heart rate, around 20 minutes of baseline conditions from the 15 participants. After the optimization process, the results suggested that the best method was bagging with random predicted selections at each split. Therefore, using 5-fold cross-validation on all the available data, we estimated the misclassification rate on 3.77% and obtained the confusion matrix. This confusion matrix shows for all the classes high values of true positives, which are the correct predictions, and they are along the principal diagonal of the matrix, and small values, when compared to the true positives, of true negatives, false positives, and false negatives. So finally, we used 70% of data to train an ensemble of 100 bagged classification trees, and the remaining 13% of data were used to test the ensemble. Both the test and the train sets were constructed preserving the original class distribution. We had obtained a high accuracy, almost 96%, which is reinforced by the high values of precision, recall, and F1 scores. And altogether, this indicates a good performance of the classifier. So, as conclusions and further research, this work targets the psychophysiological perspective of anxiety, and we had shown that it is possible to characterize physiological correlates of anxiety states. The present results ensure that feasibility to classify anxiety scores using electrodermal activity and heart rate data collected with a wrist wearable device. For further research, since wrist wearable devices are a common and minimally invasive equipment that can assess continuous physiological signals, we intend to integrate this classification task into wearable and smart sensing contexts. So, we expected to develop a mobile application that, based on the classification of anxiety states, can provide strategies to deal and cope with anxiety in real time. Moreover, to better attain the problem of anxiety classification under neutral conditions, we also intend to design a specific protocol to collect data more suitable to this purpose. And that concludes my presentation. I would like to thank you all for your attention, and I will be available for questions and answers.
Dear all, following the last presentation and discussion, now the 2020 edition of the HealthyIoT conference is almost over. This year, more than ever, we understood the critical role of science and technology for the safety of our societies and also for the improvements of the healthcare sector and services. Thanks to the knowledge that our authors and presenters shared with us, now we have a deeper understanding of how IoT may support and empower advanced healthcare solutions. Now, on behalf of the organizing committee, I have the pleasure to thank all the people who made this year's edition possible. Authors and presenters, of course, but also our panelists, all the members of the different committees involved in the organization, the reviewers, the attendees, and last but not least, our Natasha Onofrei from EAI for her invaluable professional support through all the steps of the organizations of this conference. Before we leave, I also have the pleasure to present the HealthIoT 2020 Best Paper Award to authors Vilasana Maria Vanessa, Ivan Pires Miguel, Juliana Sa, Nuno Garcia, Eftim Zavesky, Petr Lamesky and Ivan Chorbev for the paper entitled CoviHealth, a pilot study of physical activities and nutrition habits of teenagers in Central Portugal. Congratulations to the authors. They reached the highest scores after review, and so we are very happy to present them with this Best Paper Award. So, HealthyIoT 2020 now is really over. I thank you all again and hope to see you all next year. Thank you.